Thank you for listening to the Sleepy Mind channel. Olive trees are among the oldest cultivated trees in the world, quietly growing in the same landscapes where people first learned to farm, settle, and build long-lasting communities. Long before modern agriculture, olive trees were already shaping daily life, providing food, fuel, and material through steady, patient growth. Tonight, this story explores the olive tree itself, beginning with where it comes from, the conditions it prefers, and the long relationship between the tree and the people who learn to grow it. The focus stays with the physical tree, its environment, and the slow patterns that define its life. And if you like stories like these, please like and subscribe. Let's begin. Olive trees are among the oldest cultivated trees known to humans. Archaeological evidence shows that people have been growing olive trees for more than 6,000 years. This long history is not accidental. Olive trees thrive in conditions that encourage permanence rather than movement. Once established, they remain rooted in the same place for generations, producing fruit slowly and reliably over long periods of time. The tree originated in the eastern Mediterranean region. This area includes coastal and inland zones where summers are long and dry and winters are mild and wet. These seasonal patterns shape the olive tree's structure and behavior. Rather than growing quickly in short bursts, the tree adapted to conserve resources, endure dry periods, and resume steady growth when moisture returns. Olive trees grow best in warm climates with extended dry summers. Heat does not harm the tree when water is limited, but predictable. Instead, the olive tree uses warm conditions to slow growth, reduce water loss, and protect its internal systems. Long dry seasons discourage competing vegetation, allowing olive trees to dominate rocky hillsides where other plants struggle. Mild, wet winters are equally important. Winter rainfall replenishes soil moisture without exposing the tree to prolonged cold. Olive trees do not tolerate severe freezing temperatures. Extended frost can damage leaves, split wood, and kill young growth. For this reason, olive cultivation remains concentrated in regions where winters stay moderate and predictable. The seasonal rhythm of wet winters and dry summers creates a reliable cycle. During wetter months, olive trees absorb water, support leaf growth, and prepare for flowering. As summer arrives and soil dries, growth slows. Energy is conserved rather than wasted on rapid expansion. This cycle allows the tree to survive year after year without exhausting its resources. Olive trees are highly adapted to drought conditions. Their survival depends on managing water efficiently rather than accessing large quantities of it. The tree's root system extends both deep and wide into the soil. These roots search for moisture stored in lower layers and spread outward to collect water from a broad area after rainfall. Deep roots allow olive trees to access water long after surface soils have dried. Wide roots stabilize the tree on slopes and rocky terrain. Together, this root structure helps olive trees remain upright and functional in landscapes where erosion and poor soil would undermine faster-growing plants. Olive trees grow slowly compared to many fruit trees. This slow growth contributes directly to their longevity. Instead of producing soft, fast-growing wood, olive trees develop dense, resilient trunks and branches. Growth rings form gradually, strengthening the tree over time rather than stretching it quickly upward. Slow growth also limits damage during stress. When conditions become difficult, olive trees reduce activity rather than pushing through adversity. Leaves remain functional, roots stay active, and internal systems continue operating at a reduced pace. This controlled response prevents sudden failure. Because olive trees grow slowly, they reward long-term care rather than short-term intervention. A newly planted olive tree may take many years before producing fruit, but once established, it can remain productive for centuries. Some olive trees alive today are estimated to be over 1,000 years old, still producing olives season after season. Very old olive trees often continue bearing fruit even as their trunks twist, hollow, and scar with time. Rather than replacing old wood quickly, the tree reinforces existing structure and regenerates where necessary. Olive trees are evergreen, keeping their leaves throughout the year. This allows continuous photosynthesis whenever conditions permit. Leaves are narrow and leathery, designed to withstand intense sunlight and reduce water loss. The underside of each leaf is silvery in color, reflecting sunlight and limiting heat absorption. This leaf structure allows olive trees to remain active in bright, exposed environments. Even during the hottest months, leaves continue functioning without overheating. Water loss is controlled, and internal temperatures remain stable enough to support slow metabolic activity. The combination of evergreen leaves, deep roots, and slow growth defines the olive tree's approach to survival. Rather than competing aggressively for space or resources, the tree settles into environments where stability matters more than speed. Rocky soils, steep slopes, and open sun become advantages rather than obstacles. Olive trees tolerate poor soil conditions remarkably well. Fertility matters less than drainage. Too much water can harm olive trees, increasing disease risk and weakening roots. Well-drained soil allows roots to breathe and prevents prolonged saturation that would damage internal tissues. Moderate stress often improves olive quality. When water is limited but not absent, olive trees focus energy on fruit rather than excessive leaf growth. This controlled stress produces olives with more concentrated compounds, shaping flavor and oil quality later on. Olive trees grow best with consistent but limited watering. Too much water reduces fruit quality and encourages disease. Too little water triggers survival mode, slowing production. The balance between these extremes reflects the Mediterranean environments where olive trees evolved. Over centuries, people learned to work within these limits. Olive groves were planted where soil drained quickly, where slopes reduced standing water, and where sunlight remained constant. These choices shaped settlement patterns and agricultural traditions that still exist today. The olive tree's long relationship with people reflects shared patience. Both the tree and the grower invest in time rather than speed. Care given early influences outcomes decades later. This long view defines olive cultivation more than yield numbers or harvest size. At the start of its life, an olive tree establishes roots and structure before producing fruit. Years pass before the first olives appear. During this time, the tree builds capacity rather than output. Once fruiting begins, production increases gradually as the tree matures. Olive trees survive in climates that challenge many other fruit trees because they are adapted to drought rather than abundance. Long, dry summers are not an obstacle for olive trees. They are the conditions that shaped how the tree functions. Instead of relying on frequent surface moisture, olive trees manage water slowly and deliberately, maintaining internal stability when rainfall is absent for months at a time. One of the olive tree's most important adaptations is its root system. Roots grow both deep and wide, extending far beyond the visible canopy. Deep roots reach moisture stored well below the surface, while wide roots collect water from a broad area after rainfall. This combination allows olive trees to continue functioning long after shallow soil layers have dried. These roots also anchor the tree in rocky or uneven terrain. Olive trees often grow on hillsides where soil is thin and erosion is common. Wide roots stabilize the tree against wind and gravity, while deep roots secure access to water that other plants cannot reach. This structure allows olive trees to occupy landscapes that would otherwise remain sparsely vegetated. Drought conditions slow visible growth rather than stopping internal processes. When water becomes scarce, olive trees reduce expansion of new shoots and leaves. Energy is conserved rather than spent. Leaves remain functional, photosynthesis continues at a reduced rate, and internal systems stay active. This controlled slowdown prevents damage that would occur if the tree attempted to maintain rapid growth under stress. Olive trees are well adapted to intense sun exposure. Unlike plants that require shade to prevent overheating, olive trees tolerate open sunlight throughout the day. Their narrow, leathery leaves reduce surface area exposed to heat. The silvery underside of each leaf reflects sunlight, lowering leaf temperature and limiting water loss through evaporation. Sunlight plays a role in regulating growth as well. Bright conditions signal the tree to maintain conservative growth during dry periods. Instead of responding with rapid expansion, the olive tree remains steady. This restraint reduces demand on water reserves and protects internal tissues from heat stress. Slow growth is central to olive tree survival. Compared to many fruit trees, olive trees grow at a measured pace. Wood forms gradually, producing dense, resilient trunks and branches. This slow accumulation of structure strengthens the tree over time and reduces vulnerability to cracking or breakage during drought or heat. Slow growth also contributes to longevity. Because tissues develop under limited stress, olive trees avoid the weaknesses that often shorten the lifespan of faster-growing species. Growth rings form gradually, reinforcing existing wood rather than stretching it thin. This allows olive trees to live for hundreds of years while remaining productive. Drought tolerance does not mean indifference to water. Olive trees still require moisture, but they respond best to limited, consistent availability rather than frequent saturation. Overwatering can harm olive trees by suffocating roots and increasing disease risk. Waterlogged soil prevents oxygen from reaching roots, weakening the tree even when water is abundant. Moderate water stress often improves olive quality. When water is limited but not absent, olive trees focus energy on survival and fruit development rather than excessive leaf growth. Seasonal patterns support this balance. Wet winters replenish deep soil moisture and prepare the tree for flowering and fruit development. Dry summers slow growth and conserve resources. Olive trees evolved to rely on this predictable rhythm rather than constant water availability. Extreme cold disrupts the system. Olive trees do not tolerate prolonged freezing temperatures. Severe frost damages leaves, splits wood, and interrupts internal transport systems. For this reason, olive cultivation remains limited to regions where winter temperatures stay mild and freezing events are brief. Heat alone does not threaten olive trees when water management remains intact. It is the combination of excessive heat and poor water regulation that creates stress. When roots cannot access moisture, heat accelerates dehydration and weakens tissues. Olive trees avoid this outcome through root depth, leaf structure, and controlled growth. Sun exposure also influences fruit development. Olives ripen under bright conditions, accumulating oils and compounds over long periods. Shade reduces fruit quality by limiting photosynthesis and slowing ripening. For olive trees, open sun supports both survival and productivity. These adaptations explain why olive trees tolerate poor soils. Fertility matters less than drainage and exposure. Rocky soils drain quickly, preventing water accumulation around roots. This environment suits olive trees, which prioritize oxygen access over nutrient richness. Olive trees respond slowly to change. Sudden increases in watering, fertilization, or pruning do not produce immediate benefits. Instead, the tree adjusts gradually, reflecting its long-term strategy. This slow response protects internal balance, but requires patience from growers. Over centuries, people learned to match olive trees to environments that support these traits. Groves were planted on slopes, terraces, and exposed hillsides, where water drained freely and sun remained constant. These choices aligned human agriculture with the tree's natural design. The olive tree's ability to survive drought and sun reflects a broader approach to life. It avoids extremes, conserves energy, and maintains function under pressure. Climate, sun, and survival are inseparable for olive trees. Roots, leaves, growth speed, and seasonal rhythms work together to maintain stability. Each adaptation supports the others. When these elements remain aligned, olive trees continue their slow, dependable growth year after year. This survival strategy explains both the tree's longevity and its steady productivity. Olive trees do not chase rapid expansion. They settle into environments where restraint matters more than abundance. In doing so, they transform challenging landscapes into places of sustained life. Olive trees are known for their long lifespan, with many living for hundreds of years and some continuing to bear fruit after 1,000 years. This longevity is closely tied to how the tree grows and maintains its structure over time. Rather than replacing growth quickly, olive trees reinforce what already exists. Wood thickens slowly, tissues harden, and the tree builds durability through gradual change. Very old olive trees often remain productive even when their trunks become hollow or deeply twisted. Internal decay does not necessarily end the tree's ability to transport water and nutrients. Living tissues form along the outer layers of the trunk, allowing the tree to continue functioning while older wood becomes part of its structural core. This layered structure supports survival across centuries. Olive trees are evergreen, keeping their leaves throughout the year rather than shedding them seasonally. Evergreen growth allows continuous photosynthesis whenever conditions permit. Even during cooler months, olive leaves remain active, supporting basic metabolic functions. The evergreen habit also spreads demand more evenly across seasons. Instead of investing heavily in leaf regrowth each spring, olive trees maintain a stable canopy year-round. Energy can be directed toward maintenance, flowering, and fruit development, rather than repeated replacement of foliage. Olive leaves are narrow and leathery in texture. This shape reduces the surface area exposed to sun and wind, limiting water loss during hot, dry periods. The leathery surface resists damage from heat and dehydration, allowing leaves to remain functional under conditions that would stress softer foliage. The underside of olive leaves is silvery in color. This silvery surface reflects sunlight away from the leaf, reducing heat absorption. By lowering leaf temperature, the tree limits evaporation and preserves internal moisture. Reflection also protects internal tissues from excessive solar radiation during long summer days. Light interacts with olive leaves in a controlled way. Narrow leaves reduce direct exposure at midday, while still capturing sufficient light in morning and evening. The leaf's orientation and structure work together to manage energy intake rather than maximize it. Evergreen leaves also contribute to the olive tree's resilience. When environmental conditions become difficult, leaves remain in place and continue operating at reduced capacity. The tree does not need to regrow foliage after stress events, allowing faster recovery once conditions improve. This persistence supports survival through drought and heat. The structure of olive leaves influences airflow within the canopy. Narrow leaves allow air to move freely, reducing humidity buildup around branches. Improved airflow lowers the risk of fungal disease and keeps leaf surfaces dry after dew or light rain. This structural benefit supports health without additional intervention. Leaf longevity reduces waste within the tree's system. Instead of discarding leaves annually, olive trees retain them for several years. Nutrients are conserved within long-lived tissues, and replacement occurs gradually rather than all at once. This slow turnover matches the tree's overall pace. Light availability also shapes canopy form. Olive trees grow with open, irregular crowns rather than dense foliage. Gaps between branches allow sunlight to reach interior leaves, maintaining photosynthesis throughout the canopy. This openness reduces self-shading and supports even energy distribution. The evergreen canopy interacts with seasonal cycles differently than deciduous trees. During winter, olive trees continue operating at low levels rather than entering dormancy. When spring arrives, the tree is already active, allowing flowering and growth to proceed without delay. This readiness supports consistent annual rhythms. Structural stability develops alongside leaf persistence. Branches thicken slowly, supporting leaves that remain attached for years. This gradual strengthening prevents breakage under wind or fruit weight. The tree's form becomes more resilient with age, rather than more fragile. The combination of evergreen leaves and slow growth contributes to the olive tree's visible aging. Trunks twist, branches spread irregularly, and leaves continue functioning atop evolving structure. Each change reflects adaptation rather than decline. The tree adjusts without abandoning existing form. Olive leaves also protect internal systems during stress. When water is limited, leaves close stomata to reduce loss while maintaining basic function. The leathery surface limits damage during extended dry periods. This protective behavior allows the tree to remain alive when conditions would overwhelm less adapted species. The interaction between leaves and light defines much of the olive tree's character. Rather than chasing maximum growth, the tree regulates exposure carefully. Photosynthesis continues steadily, without surges. Energy intake remains balanced, supporting long-term health. Evergreen structure also supports fruit development. Leaves supply energy to flowers and fruit over extended periods. Because foliage remains in place year-round, the tree does not need to rebuild energy sources each season. As olive trees age, leaf distribution adjusts naturally. Older branches may carry fewer leaves, while new growth fills gaps. This redistribution maintains canopy function without dramatic shifts. The tree remains productive without requiring constant regeneration. The olive tree's evergreen nature connects directly to its cultural perception. Leaves remain present through seasons, symbolizing endurance and continuity. This visual persistence reflects the biological strategies that allow the tree to survive across generations. Leaves, light, and structure operate together as a system. Narrow reflective leaves manage energy and water. Evergreen growth maintains continuity. Slow structural reinforcement supports longevity. These elements cannot be separated. Each reinforces the others. This integrated design explains why olive trees thrive in exposed landscapes. Sunlight, wind, and limited water do not overwhelm the tree. Instead, these conditions align with its structure. The tree remains stable where others fail. The tree does not rush to replace what works. Leaves stay, wood hardens, and form adapts gradually. The tree continues its steady work under the same sun, season after season. Olive trees are well adapted to intense sun exposure, and much of this ability comes from how their leaves interact with light. The silvery underside of olive leaves plays a central role in this process. This pale surface reflects a portion of incoming sunlight away from the leaf, rather than absorbing it. By reflecting light, the leaf reduces heat buildup during long hours of direct sun, keeping internal temperatures lower than they would otherwise be. Lower leaf temperature directly reduces water loss. When leaves overheat, evaporation increases and moisture escapes more quickly through stomata. The reflective underside of olive leaves limits this effect, allowing the tree to conserve water even under strong sunlight. This adaptation is especially important during long, dry summers when rainfall is absent and soil moisture is limited. Sun reflection also protects internal leaf tissues. Excessive solar radiation can damage cells and interfere with photosynthesis. By reflecting part of the incoming light, olive leaves reduce stress on internal structures while still capturing enough energy to remain productive. Olive trees are therefore comfortable in open, exposed environments. They do not require shade to survive intense sunlight. Instead, their leaf structure allows them to remain functional in full sun throughout the day. This adaptation gives olive trees an advantage in landscapes where few other trees can tolerate constant exposure. The shape of olive leaves reinforces this effect. Narrow leaves present less surface area to the sun at any one moment, reducing direct heat absorption. As the sun moves across the sky, light strikes leaves at changing angles, rather than hitting broad surfaces continuously. This reduces overheating and spreads energy intake more evenly across time. Together, leaf shape and reflective surfaces create a passive cooling system. Olive trees do not rely on rapid water movement or constant transpiration to regulate temperature. Instead, they limit heat gain at the source. Intense sun exposure also influences growth patterns. Olive trees growing in full sun tend to grow slowly and steadily rather than rapidly. Bright conditions signal the tree to maintain conservative growth during dry periods. This restraint prevents excessive demand on water reserves and protects tissues from stress. While olive trees tolerate heat well, they are sensitive to cold. Prolonged freezing temperatures disrupt the systems that allow the tree to function. When temperatures drop below freezing for extended periods, water inside cells can form ice crystals. These crystals rupture cell walls, damaging leaves, branches, and internal transport tissues. Severe frost can damage or kill olive trees. Young trees are especially vulnerable, but mature trees can also suffer lasting harm. Frost damage often appears as blackened leaves, split bark, and dead branches. Even if the tree survives, recovery can take years. Cold damage interferes with water and nutrient movement. When internal transport tissues are damaged, roots may still absorb water, but it cannot reach leaves effectively. This creates stress even after temperatures rise again. The tree must redirect energy toward repair rather than growth or fruit production. Olive trees do not have strong dormancy mechanisms like some cold-adapted species. They remain metabolically active through much of the year. This makes them less capable of shutting down internal processes during cold periods. When freezing occurs, active tissues are more easily damaged. For this reason, olive cultivation remains limited to regions with mild winters. Brief cold spells may be tolerated, but prolonged freezing poses serious risk. Traditional olive-growing regions share a common pattern of moderate winter temperatures and minimal frost. Cold sensitivity also shapes where olive trees are planted within landscapes. Trees are often placed on slopes rather than valley bottoms. Cold air settles in low areas, increasing frost risk. Slopes allow cold air to drain away, reducing exposure. Sun exposure and cold risk interact. Open, sunny sites warm quickly during the day, but can cool rapidly at night. Olive trees benefit from locations where daytime warmth is balanced by protection from extreme nighttime cold. Stone walls, terraces, and proximity to bodies of water can moderate temperature swings. When frost does occur, olive trees respond slowly. Damaged tissues do not regenerate quickly. New growth may emerge from unaffected areas, but overall structure can be altered permanently. This slow recovery reinforces the importance of site selection and long-term planning. The contrast between heat tolerance and cold sensitivity defines the olive tree's climatic range. The tree thrives where sunlight is abundant and winters remain gentle. Outside this range, survival becomes uncertain. Sun reflection allows olive trees to endure exposure that would overwhelm many species. Cold intolerance prevents them from expanding into regions with harsh winters. Together, these traits confine olive trees to specific environments where their adaptations function as intended. These limits are not weaknesses, they reflect specialization. Olive trees evolved under consistent patterns of sun and temperature. Within those patterns, they perform reliably for centuries. Outside them, stress accumulates quickly. The relationship between sun and cold also influences seasonal rhythms. Bright, dry summers slow growth and conserve water. Mild winters allow internal systems to continue operating at reduced levels. Sun reflection and cold limits shape every stage of the olive tree's life. Leaves regulate energy intake. Tissues tolerate heat but not ice. Growth proceeds under bright skies and pauses when temperatures threaten internal stability. These adaptations allow olive trees to occupy exposed landscapes confidently while remaining vulnerable to specific extremes. The balance between tolerance and sensitivity defines where the tree belongs and how it survives. By reflecting sunlight and avoiding cold damage, olive trees maintain steady internal conditions. This steadiness supports long life, consistent growth, and dependable fruit production under the right circumstances. The tree does not seek shelter from the sun. It uses light as a constant companion. At the same time, it avoids environments where cold dominates. Within this narrow but stable range, the tree continues its slow, resilient work year after year. Olive trees produce small, creamy white flowers that appear in large numbers each spring. These flowers form in loose clusters along the branches, emerging from buds that developed during the previous season. When flowering begins, an olive tree can appear lightly dusted with pale color, as thousands of blossoms open over a relatively short period of time. Flowering usually occurs in spring, after winter rains have replenished soil moisture and temperatures have begun to rise. The timing is closely linked to seasonal conditions. If winter is too warm, flowering may be reduced. If spring temperatures fluctuate sharply, blossoms may be damaged before pollination can occur. Olive trees depend on a narrow window of stable weather for flowering to succeed. Not all olive flowers develop into olives. In fact, only a small percentage of blossoms ever become fruit. This is a normal and expected pattern, rather than a sign of failure. Olive trees produce many more flowers than they can support as fruit, allowing the tree to select a limited number of successful outcomes without exhausting its resources. This low fruit set protects the tree. Developing olives require energy, water, and nutrients over many months. If every flower became fruit, the tree would be unable to sustain growth and survival at the same time. By allowing most flowers to fall away, the tree concentrates its resources on a manageable number of developing olives. Olive trees are wind-pollinated rather than insect-pollinated. Instead of relying on bees or other insects, olive trees release large quantities of lightweight pollen into the air. Wind carries this pollen between nearby trees, allowing fertilization to occur when pollen reaches receptive flowers. Wind pollination suits the olive tree's environment. Olive groves are often open and exposed, allowing air to move freely through the canopy. Narrow leaves and open branch structure reduce obstruction, helping pollen travel efficiently. This system does not depend on insect populations or specific pollinator behavior. Cross-pollination often improves fruit production. Pollen from a different olive tree can increase the likelihood that flowers will develop into fruit. For this reason, many olive groves contain multiple varieties planted close together. This diversity increases pollen availability and improves overall yield. Some olive varieties are self-fertile, meaning they can produce fruit using their own pollen. However, even self-fertile trees often benefit from nearby companions. Cross-pollination tends to produce more consistent results, especially under variable weather conditions. Other olive varieties require nearby trees for pollination. Without compatible pollen sources, these trees may flower heavily but produce little fruit. Growers must consider pollination compatibility when planning groves, as poor placement can limit production for decades. Flowering success is sensitive to weather conditions. Strong winds during flowering can disperse pollen too quickly, reducing fertilization. Rain can wash pollen from the air or damage delicate blossoms. Sudden cold snaps can interrupt the process entirely. Because flowering occurs over a short period, these weather effects have lasting consequences. A single week of poor conditions can reduce fruit production for the entire year. Olive trees do not compensate later in the season by producing new flowers. Once pollination occurs, the fertilized flower begins developing into an olive. Most blossoms fall away, leaving behind small developing fruit on selected stems. This transition happens quietly, without dramatic visual change. The tree manages this shift carefully. Energy is redirected from maintaining flowers to supporting young fruit. Leaves supply sugars through photosynthesis, while roots provide water and minerals. Growth proceeds slowly rather than rapidly. The limited number of developing olives reflects long-term strategy. By controlling fruit load, the tree maintains balance between current production and future health. This restraint supports longevity and reduces stress. Flowering patterns also influence the tree's tendency toward alternate bearing. Heavy flowering and fruiting one year may be followed by lighter production the next. This cycle allows the tree to recover and rebuild reserves before producing again. Proper pruning can influence flowering success. By improving light penetration and airflow, pruning supports healthy bud development. Branches that receive sufficient light during the previous year are more likely to produce flowers. Air circulation during flowering reduces humidity around blossoms. This lowers the risk of fungal disease and supports pollen movement. Open canopies allow wind to carry pollen efficiently between trees. Olive flowers themselves are simple in structure. They are not designed to attract insects with color or scent. Their role is functional rather than decorative, aligned with wind pollination rather than visual appeal. The simplicity of olive flowers reflects the tree's overall approach. Resources are invested in durability and longevity rather than elaborate reproductive displays. The tree relies on abundance and probability rather than precision. Flowering also reflects the olive tree's slow pace. Buds form over long periods, influenced by conditions months earlier. Stress during the previous summer or autumn can reduce flowering the following spring. This delayed response means management decisions have long-term effects. Water stress, pruning, or disease may not show immediate impact, but can influence flowering well into the future. Olive trees do not rush reproduction. They wait for favorable conditions and proceed cautiously. The contrast between abundant flowers and limited fruit defines olive reproduction. Thousands of blossoms open. Only a few persist. This imbalance protects the tree while ensuring some reproduction succeeds. Wind pollination, low fruit set, and weather sensitivity work together to shape olive yields. These factors explain why harvests vary from year to year, even in well-managed groves. Flowering is therefore a moment of possibility rather than certainty. The olive tree prepares carefully, releases pollen, and allows outcomes to unfold. Each successful olive begins as a rare outcome among many attempts. That rarity carries forward through the growing season, shaping how much fruit the tree ultimately supports. Flowering and pollination mark the transition from preparation to production. The tree has spent months building capacity. In spring, it tests conditions briefly and commits only when circumstances allow. This cautious commitment supports the olive tree's endurance. It produces fruit without compromising survival, balancing reproduction with long-term stability. Olive trees rely on a narrow window of favorable conditions for pollination to succeed, even though they produce large amounts of pollen. Wind carries pollen between trees, but success depends on timing, air movement, and weather stability during a brief period each spring. Small changes in these conditions can determine whether a season produces a full crop or very little fruit. Pollination success begins with the release of pollen from flowering branches. Olive trees shed pollen into the air in large quantities, but pollen grains remain viable only for a limited time. If wind carries pollen too far, it may disperse before reaching receptive flowers. If air movement is too weak, pollen may settle close to the source without reaching neighboring trees. Weather conditions during flowering strongly influence this process. Calm, dry days with gentle air movement allow pollen to remain airborne long enough to reach receptive flowers. Excessive wind, however, can reduce pollination success by scattering pollen too quickly and unevenly across the landscape. Strong gusts may lift pollen high into the air, carrying it beyond effective range. Rain during flowering presents another challenge. Moisture causes pollen grains to clump and fall out of the air more quickly. Rain can also wash pollen from flowering branches before it has a chance to travel. Even brief rainfall during peak flowering can significantly reduce fertilization rates. Temperature plays a role as well. Pollination occurs most effectively within a moderate temperature range. Cool temperatures slow pollen release and reduce flower receptivity. Excessive heat can shorten the lifespan of pollen grains and stress flowers before fertilization occurs. Olive trees are sensitive to both extremes during this period. Because flowering lasts only a short time, there is little opportunity for recovery if conditions are poor. Olive trees do not produce multiple waves of flowers throughout the season. Once the flowering window passes, pollination potential for that year is set. This makes olive production highly dependent on a small number of days each spring. Weather sensitivity contributes to year-to-year variation in olive yields. Even well-managed groves can experience large fluctuations in production due to unfavorable pollination conditions. This variability is a normal part of olive cultivation, rather than a sign of poor care. Cross-pollination can improve resilience to weather variation. When multiple compatible varieties are present, pollen availability increases. A greater diversity of pollen sources raises the chance that some fertilization will occur, even if conditions are not ideal. This is why traditional groves often contain mixed plantings rather than a single variety. Self-fertile olive varieties still respond to weather conditions. Even when pollen comes from the same tree, it must still travel through the air to reach receptive flowers. Wind, temperature, and moisture continue to influence success, regardless of compatibility. Weather conditions in the months leading up to flowering also affect pollination outcomes. Stress during the previous growing season can reduce flower quality and pollen production. Drought, extreme heat, or nutrient imbalance may limit the tree's ability to form viable flowers, reducing pollination potential before flowering even begins. Spring weather patterns therefore interact with earlier conditions. A tree that experienced stress the previous year may flower less heavily or produce weaker pollen. Even ideal weather during flowering may not fully compensate for earlier strain. Pollination success also influences the tree's internal balance. When fertilization rates are high, the tree must support more developing fruit. When rates are low, the tree conserves energy for growth and recovery. This adjustment happens automatically, reflecting the tree's long-term strategy. Low pollination success does not necessarily harm the tree. In fact, reduced fruit load can benefit future productivity by allowing the tree to rebuild reserves. This contributes to the phenomenon of alternate bearing, where heavy crop years are followed by lighter ones. Weather sensitivity reinforces the olive tree's conservative approach. The tree does not attempt to force fruit development under marginal conditions. Instead, it responds to environmental signals and proceeds only when circumstances allow. This responsiveness explains why olive cultivation rewards observation rather than intervention. Growers cannot control wind or rainfall during flowering. They can only position trees appropriately, select compatible varieties, and manage canopy structure to support airflow. Open canopies improve pollination by allowing wind to move freely through flowering branches. Proper pruning reduces turbulence that can disrupt pollen movement and prevents flowers from being trapped in dense foliage. This structural management improves the odds of success without overriding weather influence. Terrain also affects pollination. Groves planted on slopes experience different wind patterns than those in valleys. Elevated positions may receive more consistent air movement, while low areas can trap moisture and reduce pollen viability. Traditional planting locations reflect generations of observation. Weather sensitivity also limits the geographic expansion of olive trees. Regions with frequent spring rain, unstable temperatures, or unpredictable wind patterns may struggle to produce consistent crops, even if trees survive there. Pollination success, rather than tree survival, often determines long-term viability. As climate patterns shift, pollination weather may become less predictable. Changes in rainfall timing or temperature variability can narrow the window of favorable conditions. This increases uncertainty for growers and may intensify yield fluctuations. Olive trees respond slowly to these changes. Because they are long-lived, they cannot quickly adapt flowering behavior to new climate regimes. Trees planted decades earlier continue following patterns shaped by historical conditions. Despite this sensitivity, olive trees persist because their strategy emphasizes endurance over output. A poor pollination year does not threaten survival. The tree adjusts and continues growing, preparing for future opportunities. Pollination success therefore represents opportunity rather than obligation. When conditions align, fruit develops. When they do not, the tree waits. Weather sensitivity also shapes cultural expectations around olive harvests. Variability is accepted as part of the system. Harvest size reflects environmental balance rather than effort alone. Pollination and weather together form a gatekeeper stage in olive reproduction. Many factors must align briefly for success. When they do, fruit development proceeds slowly and steadily. The tree's response to this uncertainty reflects its overall design. It survives by adapting to variability rather than resisting it. Pollination success emerges from cooperation between biology and environment. Olives are technically a type of fruit known as a drupe. This places them in the same botanical category as peaches, cherries, and plums. Like other drupes, olives develop from a single flower and contain a hard inner pit that protects the seed. This structure defines how olives grow, mature, and are processed after harvest. The outer layer of an olive is the skin, which changes in color and texture as the fruit ripens. Beneath the skin is the fleshy portion of the fruit, which surrounds the pit. Inside the pit is the seed, which carries the genetic material for a new olive tree. This simple structure supports a long, slow development process that unfolds over many months. Each olive contains a single hard pit. The pit is thick and rigid, designed to protect the seed from damage during growth and after the fruit falls. This protective shell also limits how the fruit can be eaten or processed. Unlike soft fruits that can be consumed directly, olives require preparation before they are palatable. Fresh olives are naturally very bitter. They cannot be eaten directly off the tree. This bitterness is not a flaw. It is a defensive trait that discourages animals from consuming the fruit before the seed is ready. The bitterness comes from compounds called oleuropeins, which are present in high concentrations in fresh olives. Oleuropeins affect taste immediately. Even a small amount creates an intense bitter sensation that overwhelms other flavors. This chemical defense protects the seed inside the pit by making the fruit unappealing to most animals. Without this protection, olives would be eaten before they could complete development. As olives grow on the tree, they remain firm and inedible despite their increasing size. The tree does not attempt to make the fruit attractive at this stage. Instead, it invests energy in developing oils and compounds inside the flesh, storing resources that will later influence flavor and quality. The olive's classification as a drupe also explains its slow ripening. Like other stone fruits, olives develop gradually, responding to seasonal conditions rather than short-term changes. Ripening is influenced by temperature, sunlight, and water availability over extended periods. Color change is one visible sign of ripening. Olives often begin green and gradually darken to purple or black as they mature, depending on variety. This color shift reflects changes in pigments within the skin and internal chemistry within the flesh. However, color alone does not indicate readiness for harvest. Texture, oil content, and flavor compounds continue to evolve beyond surface appearance. The flesh of the olive contains oil rather than juice. This distinguishes olives from many other fruits. As the fruit matures, oil accumulates within the flesh, stored in small droplets inside cells. These oils are the source of olive oil extracted later through crushing and separation. Because oil accumulation occurs slowly, olives remain on the tree for long periods. The tree supports this extended development by supplying water and nutrients through the stem. During this time, the fruit remains bitter and firm, protected by chemical defenses and physical structure. The hard pit plays a role beyond seed protection. It also limits how the fruit can be damaged by pressure or pests. The pit maintains the shape of the fruit and prevents collapse as oils accumulate in the surrounding flesh. This internal support allows olives to hang on the tree without deforming. Different olive varieties produce fruits with varying sizes, shapes, and oil content. Some olives are small and dense, while others are larger, with thicker flesh. These differences influence how olives are used, whether for oil production or curing for table consumption. Despite these variations, all olives share the same basic structure. Skin, flesh, pit, and seed work together to protect and nourish the developing seed. The tree's role is to manage this process slowly, balancing fruit development with overall health. The bitterness of fresh olives remains until human intervention. The tree does not remove or reduce oleuropeins on its own. This means that olives must be cured before they can be eaten. Curing processes target these bitter compounds, breaking them down or drawing them out of the flesh over time. The need for curing explains why olives have been processed for thousands of years. Without curing, the fruit remains inedible. This necessity shaped early food practices and led to regional traditions that persist today. As fruit, olives reflect the olive tree's overall strategy. They are not designed for immediate consumption. They require patience, time, and transformation. This mirrors the tree's slow growth and long lifespan. The olive's identity as a drupe also explains why it responds strongly to environmental stress. Drought, excess water, or temperature extremes can alter fruit size, oil content, and flavor. Because development takes months, conditions across seasons shape the final outcome. Fruit development also interacts with the tree's alternate bearing pattern. In heavy crop years, resources are divided among many developing olives, which may remain smaller. In lighter years, fewer olives may grow larger and accumulate more oil. This variation reflects internal balance rather than inconsistency. Olives remain attached to the tree until harvest. They do not drop easily when ripe. This allows growers to choose harvest timing based on intended use rather than natural release. Olives harvested earlier produce different flavors and oils than those left to mature longer. The fruit structure supports this flexibility. Firm flesh and a protective pit allow olives to remain on the tree without spoiling. Chemical defenses continue operating, protecting the fruit until it is removed. As fruit, olives represent stored potential rather than immediate reward. Their bitterness signals that transformation is required. Their oil content indicates value that emerges only through careful handling. The tree produces fruit that resists consumption, demands processing, and rewards patience. This relationship between tree and fruit reflects long-term survival rather than short-term appeal. Each olive carries within it the slow work of the tree. Months of sunlight, controlled water use, and careful growth are stored in its flesh. The pit protects the seed, while bitterness protects the whole. As fruit, olives are shaped by restraint. They are not meant to be eaten as they are found. They are meant to be transformed. This expectation has guided how people interact with olive trees for thousands of years. The olive fruit therefore completes one stage of the tree's cycle while beginning another. From growth to harvest to curing or pressing, the fruit moves from biological protection to human use, carrying the tree's slow rhythm forward. The bitterness of fresh olives comes from compounds called oleuropeins, which are present in high concentrations in the fruit while it is still on the tree. These compounds create an immediate, intense bitter taste that makes fresh olives inedible. The bitterness is not accidental. It functions as a defense, discouraging animals from eating the fruit before the seed inside the pit is fully developed. Oleuropeins are distributed throughout the olive's flesh. Even small amounts are enough to overwhelm other flavors. As long as these compounds remain intact, the fruit cannot be eaten comfortably. The olive tree does not reduce this bitterness on its own. It persists through ripening, remaining present whether the olive is green or dark. Because of this natural bitterness, olives must be cured before they can be eaten. Curing is the process that removes or reduces oleuropeins, transforming the fruit into something palatable. Without curing, olives remain hard, bitter, and unpleasant, regardless of how mature they appear. Curing does not happen quickly. It requires time and controlled conditions that allow bitter compounds to break down or leach out of the fruit. This slow transformation reflects the olive tree's broader rhythm, where change happens gradually rather than suddenly. Different cultures developed curing methods that suited their climate, resources, and tastes. Over centuries, these methods became traditions passed down through families and regions. Although techniques vary, the goal is always the same: to reduce bitterness while preserving the fruit's structure and flavor. One common curing method is brining. Olives are submerged in salt water for extended periods. Salt draws bitter compounds out of the flesh through osmosis. As the olives sit in the brine, oleuropeins gradually move from the fruit into the surrounding liquid. The brine is often changed or refreshed as bitterness is released. Brining also introduces fermentation. Naturally occurring microorganisms begin to act on sugars in the olive, producing acids that contribute to flavor development. This fermentation happens slowly, shaping taste over weeks or months rather than days. Another curing method is dry curing. In this process, olives are packed in salt without added water. Salt draws moisture out of the fruit, concentrating flavors while reducing bitterness. Dry curing produces olives with a wrinkled texture and intense taste, reflecting a more concentrated transformation. Lye curing is a faster method used in some regions. Olives are soaked in an alkaline solution that chemically breaks down oleuropeins. This process reduces bitterness more quickly than brining or drying. After lye treatment, olives must be thoroughly rinsed and often placed in brine to restore balance and develop flavor. Although lye curing speeds up bitterness removal, it still requires careful control. Excessive exposure can damage texture or strip flavor. Even after lye treatment, olives benefit from time in brine to stabilize and develop complexity. Curing methods vary by region because climate influences how olives respond to treatment. Warm temperatures accelerate fermentation and chemical reactions, while cooler conditions slow them. Traditional methods evolved to match local environments, ensuring reliable results over time. Regardless of method, curing always takes time. Even the fastest processes require days or weeks. Slower methods may take several months. During this period, olives change gradually. Bitterness softens, texture shifts, and flavor deepens. The length of curing influences the final taste. Shorter curing leaves more bitterness and sharper flavors. Longer curing produces milder, more rounded olives. This variation allows different styles to develop, ranging from bold and intense to smooth and subtle. Curing also preserves olives. Salt, acidity, and reduced moisture inhibit spoilage, allowing olives to be stored for long periods. This preservation was essential in early agricultural societies, where seasonal harvests needed to last through the year. The need for curing shaped how olives were valued. Unlike fruits that could be eaten immediately, olives required labor, knowledge, and patience. This increased their importance as a stored food rather than a casual snack. Curing transforms olives without removing their identity. The fruit remains firm, the pit intact, and the oils preserved. What changes is the balance of compounds within the flesh. Bitterness recedes, allowing other flavors to emerge. The slow pace of curing mirrors the olive tree's growth. Just as the tree takes years to produce fruit, the fruit itself requires time before it becomes edible. Curing also highlights the relationship between human intervention and natural design. The olive tree produces fruit that cannot be eaten as it is. Humans learn to work with this constraint, developing processes that respect the fruit's structure while making it usable. Flavor development during curing is cumulative. Each week alters the balance slightly. Temperature, salt concentration, and time interact to shape the outcome. Small adjustments can produce noticeably different results. Because curing is gradual, it allows careful monitoring. Olives can be tasted and adjusted as bitterness declines. This flexibility supports consistency and quality control across batches. The persistence of traditional curing methods reflects their effectiveness. Despite modern alternatives, many producers continue using techniques developed centuries ago. These methods remain reliable because they align with the fruit's chemistry. Curing also separates olives intended for eating from those pressed for oil. Table olives are cured to preserve flesh and texture. Olives for oil may be processed differently, as bitterness contributes less directly to oil flavor. The transformation from bitter fruit to edible olive marks a significant shift. The fruit moves from biological defense to human food. This shift depends entirely on controlled time and technique. Bitterness never disappears completely. Even cured olives retain a trace of their original sharpness. This remaining bitterness contributes to character and balance, preventing the fruit from becoming bland. The curing process, therefore, does not erase the olive's nature, it moderates it. Defensive compounds are reduced to levels that add depth rather than repulsion. This moderated bitterness connects olives to olive oil, which also retains subtle bitter notes. Both products reflect the same chemical origins, expressed differently through processing. Curing makes olives edible, but it also makes them durable. Properly cured olives can be stored, transported, and shared long after harvest. This durability helped olives become a staple across regions. The time invested in curing extends the value of the harvest. Olives picked over a short season become food that lasts for months. This transformation supports long-term planning rather than immediate consumption. Bitterness and curing define olives as a food shaped by restraint. Nothing happens instantly. Each stage requires waiting and observation. The result reflects accumulated care. Curing completes the olive's transition from protected fruit to human nourishment. The tree produces the raw material. Time and technique reveal its potential. This transformation sets the stage for later uses, including pressing olives into oil. In both cases, bitterness is managed rather than eliminated, allowing flavor to emerge slowly. Bitterness and curing therefore form a central chapter in the olive story. Without them, the fruit remains inaccessible. With them, olives become a lasting, versatile food shaped by patience and practice. Olive trees do not produce fruit quickly. After planting, several years pass before the first olives appear. Most olive trees begin yielding fruit between 5 and 10 years of age. During this early period, the tree focuses on establishing roots, strengthening its trunk, and developing a stable canopy rather than producing harvestable fruit. As the tree matures, fruit production increases gradually. Early harvests are often light and irregular. With time, the tree's internal systems become more efficient. Roots expand into surrounding soil, branches strengthen, and leave supply energy more consistently. This slow progression allows the tree to support fruit without compromising long-term health. Olive trees often follow a pattern known as alternate bearing. In one year, the tree produces a heavy crop. In the following year, fruit production may drop noticeably. This alternating rhythm reflects how the tree balances energy use across seasons rather than a flaw in management. Heavy harvest years place significant demand on the tree. Developing olives require water, sugars, and nutrients over many months. When fruit load is high, resources are diverted towards supporting olives rather than building reserves. After such a year, the tree may enter a lighter production phase to recover. During lighter years, the tree rebuilds internal reserves. Leaves continue photosynthesis, roots store nutrients, and new buds form for future flowering. This recovery phase prepares the tree for another productive cycle. Alternate bearing allows the olive tree to avoid exhaustion and maintain productivity over decades. This pattern is influenced by environmental conditions. Adequate water, stable temperatures, and good light exposure can soften extremes between heavy and light years. Severe stress during a heavy year may deepen the following decline. Conversely, balanced conditions can moderate fluctuations. Proper pruning plays a role in managing yield patterns. By controlling branch density and distributing growth evenly, pruning helps regulate the number of flowering sites. Removing excess or shaded branches reduces competition for resources and improves consistency in fruit production. Pruning also improves air circulation and light penetration. Branches that receive sufficient light are more likely to produce healthy flowers and fruit. Improved airflow reduces disease risk, protecting both current and future yields. Even with careful management, alternate bearing cannot be eliminated entirely. It is embedded in the olive tree's biology. Management practices influence the degree of variation rather than removing it. Olive trees are naturally resistant to many pests, which supports long-term yield stability. Thick leaves, dense wood, and chemical defenses reduce vulnerability. However, olive trees remain susceptible to certain insects and fungal diseases, especially when stressed. Disease pressure can influence yield patterns. Infection during flowering or early fruit development can reduce harvest size. Damage to leaves or branches may also affect the following year's production by reducing bud formation. Yield also changes as the tree ages. Young mature trees often increase production steadily for many years. Middle-aged trees may reach peak productivity. Very old trees can continue producing olives, but yields may become lower or more irregular. Despite reduced output, old olive trees often remain valuable. Their fruit may contain higher oil concentrations or distinctive flavor characteristics. Longevity allows trees to continue contributing even as structure changes. The relationship between age and yield reflects the olive tree's conservative growth strategy. Rather than maximizing output at any one stage, the tree spreads productivity across a long lifespan. Environmental stress affects yield patterns directly. Drought during flowering or fruit development reduces harvest size. Excess water increases disease risk and weakens roots. Olive trees respond to these conditions by adjusting fruit load rather than failing outright. Yield variability is therefore expected. Harvest size reflects the combined effects of age, weather, pruning, and recovery cycles. This variability does not indicate poor management when the tree remains healthy. Harvest timing also influences perceived yield. Olives left on the tree longer increase oil content, but may reduce total fruit count due to natural drop or damage. Earlier harvests may produce more fruit by number, but lower oil yield. Growers choose harvest timing based on intended use. Olives grown for oil may be harvested later, while table olives are often picked earlier to preserve firmness. These choices affect yield measurements without altering the tree's biological rhythm. Olive trees respond slowly to changes in management. Adjustments made in one year may not show results until several seasons later. This delayed response requires patience and long-term planning. Yield patterns are also shaped by site selection. Trees planted in well-drained soil with consistent sun exposure tend to show more stable production. Poor sites amplify alternate bearing and stress effects. The olive tree's ability to regulate yield protects long-term survival. Rather than producing maximum fruit every year, the tree adjusts output to match available resources. The alternating rhythm of heavy and light years becomes part of the grove's character. Over time, growers learn to anticipate these cycles and plan labor and processing accordingly. Yield patterns also influence cultural traditions around olive harvest. Some years bring abundant pressing and storage. Other years bring quieter harvests and recovery. This variability is accepted rather than resisted. The olive tree's approach to maturity and yield reflects its broader philosophy. Growth is slow, production is measured, recovery is built in. These traits allow the tree to remain productive across generations. By balancing fruit load with survival, olive trees maintain stability over time. They do not sacrifice longevity for short-term abundance. Maturity brings reliability rather than excess. Yield patterns reflect internal balance rather than randomness. Olive trees continue producing fruit according to their long-term rhythm. Pruning plays a central role in maintaining the health and productivity of olive trees. Because olive trees grow slowly and live for many decades, their structure must be managed carefully over time. Pruning is not about forcing rapid growth. It is about guiding the tree's natural form so that light, air, and energy move efficiently through the canopy. Olive trees develop dense branching if left entirely unpruned. Over time, this density can reduce light penetration into the interior of the tree. Shaded branches receive less energy, weakening leaf function and reducing the formation of healthy flower buds. Pruning opens the canopy, allowing sunlight to reach more of the tree's structure. Improved light exposure supports balanced growth. Branches that receive consistent light produce stronger leaves and more reliable flowering. Light also helps regulate internal rhythms, ensuring that buds formed one season develop properly in the next. Pruning therefore influences future production as much as current health. Airflow is another critical outcome of pruning. Dense canopies trap moisture around leaves and branches, especially after rain or dew. When air cannot circulate freely, humidity remains high, creating favorable conditions for fungal disease. By removing crowded or overlapping branches, pruning allows air to move through the tree more easily. Better airflow helps leaf surfaces dry more quickly. This reduces the time that moisture remains on leaves and flowers, lowering the risk of infection. Olive trees are naturally resistant to many pests and diseases, but prolonged damp conditions can still create problems. Pruning supports the tree's natural defenses by improving its environment. Pruning also removes weak, damaged, or diseased wood. Branches that are broken, cracked, or infected can drain energy from the tree without contributing to growth or production. Removing these parts allows the tree to redirect resources toward healthy tissue. This selective removal strengthens overall function. Timing matters in pruning. Olive trees respond best when pruning aligns with their growth cycle. Heavy pruning during active growth can stress the tree, while pruning during dormancy or low activity periods allows recovery without disrupting flowering. Careful timing preserves balance rather than creating shock. Pruning influences the shape of the olive tree. Traditional forms encourage an open center with branches extending outward rather than upward. This structure exposes interior branches to light and air while keeping fruit within reach for harvesting. The form reflects both biological needs and practical considerations. An open structure also reduces mechanical stress. Branches that are well spaced experience less rubbing and breakage during wind. Weight from developing fruit is distributed more evenly across the tree. This reduces the risk of branch failure and long-term damage. Pruning helps manage alternate bearing as well. By moderating the number of flowering sites, pruning can reduce extreme swings between heavy and light harvest years. Removing excess growth during heavy years helps the tree conserve energy and prepare for future production. The relationship between pruning and yield is gradual. Results are not immediate. A pruning decision made one year may influence flowering and fruiting several seasons later. This delayed response requires patience and consistent practice rather than reactive adjustments. Olive trees respond slowly to change. Excessive pruning can weaken the tree, reducing leaf area too much and limiting photosynthesis. Insufficient pruning allows overcrowding and stress. The goal is moderation, adjusting structure incrementally over time. Healthy pruning maintains a balance between old and new wood. Older branches provide structural stability, while new growth supports flowering and fruit development. Removing too much old wood can reduce resilience. Removing too little new growth can limit production. Skilled pruning preserves this balance. Airflow through the canopy also affects temperature regulation. Moving air helps dissipate heat during warm periods, preventing excessive warming of interior branches. This supports leaf function and reduces water stress during dry conditions. Pruning supports access for observation and care. Open canopies make it easier to monitor tree health, identify early signs of stress, and apply management practices effectively. Visibility reduces the chance that problems develop unnoticed. The health benefits of pruning extend below ground. By regulating canopy size, pruning helps match root capacity with leaf demand. Excessive leaf area can strain water uptake, while balanced structure supports efficient root function. Olive trees recover well from careful pruning. New shoots emerge gradually from existing wood, filling gaps without overwhelming the structure. This regenerative ability allows the tree to adjust over time while maintaining continuity. However, olive trees are slow to recover from severe mistakes. Deep cuts or removal of major structural branches can alter growth permanently. Such changes may reduce productivity for years. This reinforces the need for restraint and long-term planning. Pruning also influences disease spread. Removing infected wood reduces sources of pathogens. Improved airflow and light reduce conditions favorable to disease development. Together, these effects support long-term health without reliance on chemical intervention. The relationship between pruning and health reflects the olive tree's broader strategy. It thrives under steady, thoughtful management rather than aggressive control. Each cut should serve a clear purpose within the tree's natural rhythm. Over centuries, pruning techniques evolved alongside olive cultivation. Traditional methods reflect accumulated observation rather than fixed rules. Growers learned how trees respond over time and adjusted practices accordingly. Pruning is therefore both an art and a discipline. It requires understanding how olive trees grow, how they allocate energy, and how they respond to change. Mistakes cannot be corrected quickly, but careful decisions accumulate benefits over decades. Airflow, light, and structure are inseparable in olive tree health. Pruning shapes all three. When done well, it supports flowering, reduces disease risk, and preserves longevity. When neglected or misapplied, problems compound slowly. The slow pace of olive trees means that health is maintained through prevention rather than correction. Pruning creates conditions that reduce stress before it appears. This proactive approach aligns with the tree's long life. Healthy olive trees do not appear dramatically different after pruning. Changes are subtle. Canopies open slightly. Branches breathe. Light reaches deeper. Over time, these small adjustments produce stable growth and consistent production. Pruning supports the olive tree's ability to endure. By guiding structure rather than forcing change, it allows the tree to remain productive across generations. This quiet guidance reflects the tree's preference for balance over intensity. The practice of pruning connects human care directly to tree health. Each decision influences airflow, light, and growth for years to come. This long-term impact defines the role of pruning in olive cultivation. Pruning, airflow, and health form a continuous relationship. Each supports the others. When managed together, they create conditions in which olive trees continue their slow, resilient growth under open skies. Olive oil is produced by transforming whole olives into a liquid extracted from the fruit's flesh. This process begins after harvest, when olives are taken from the tree and prepared for pressing. Timing matters. Olives begin changing as soon as they are picked, and oil quality depends on how quickly and carefully the fruit is handled. The first step in making olive oil is crushing the olives into a paste. Whole olives, including skin, flesh, and pit, are ground together. Crushing breaks open the cells in the flesh, releasing tiny droplets of oil. The pit contributes mechanical resistance, helping rupture cell walls without adding flavor. Traditionally, olives were crushed using stone mills that slowly rotated over the fruit. Modern methods use metal crushers, but the goal remains the same. The fruit is reduced to a uniform paste that contains oil, water, and solid plant material. This paste holds the oil in suspension rather than free-flowing form. Once the paste is formed, it must be mixed gently. This stage is called malaxation. Slow mixing allows small oil droplets to combine into larger ones. As droplets merge, oil becomes easier to separate from water and solids. Mixing must be controlled carefully to avoid excessive heat or oxidation. Temperature control is critical during malaxation. Lower temperatures preserve flavor, aroma, and nutritional compounds. When olive oil is described as cold-pressed, it means the oil was extracted without significant added heat. Cooler processing protects delicate compounds that define quality. After mixing, the oil must be separated from the paste. Modern systems use centrifuges to spin the paste rapidly, separating components by density. Oil, water, and solids separate into distinct layers. The oil is then drawn off for filtering or settling. Separation does not change the oil's chemistry. It simply isolates what the olive tree has already produced. The quality of the oil depends largely on the condition of the fruit and the care taken during processing, rather than on complex refinement. Olive oil quality is closely tied to fruit ripeness. Olives harvested earlier tend to produce oil with sharper, more intense flavors. These oils often contain higher levels of certain compounds that contribute bitterness and pungency. Olives harvested later produce milder, rounder oils with softer profiles. Ripeness also affects oil yield. As olives mature, oil content increases. Later harvests often produce more oil by volume, but this can come at the cost of reduced complexity. Growers choose harvest timing based on intended style rather than maximum extraction. The oil extracted from olives consists mostly of monounsaturated fats. These fats are stable and resistant to oxidation compared to other types. This stability contributes to olive oil's long shelf life and its reputation for supporting health when consumed regularly. Olive oil also contains antioxidants and other minor compounds. These contribute flavor and help protect the oil from degradation. The concentration of these compounds depends on variety, growing conditions, and harvest timing. Careful processing preserves them. Filtration or settling removes remaining water and fine solids from the oil. Some producers filter immediately, while others allow oil to settle naturally before decanting. Both methods aim to stabilize the oil and prevent spoilage. Freshly extracted olive oil often appears cloudy due to suspended particles. Over time, these particles settle or are removed, leaving clear oil. Cloudiness does not necessarily indicate poor quality, but stability improves once solids are removed. Olive oil does not require chemical refinement when produced properly. Extra virgin olive oil is defined by mechanical extraction and low acidity. This reflects minimal processing and preservation of natural compounds. The process from fruit to oil is direct. There is no fermentation or cooking involved in producing high-quality olive oil. This simplicity means that flaws in fruit quality or handling are carried directly into the final product. Speed matters after harvest. Olives left sitting too long before processing can begin to ferment unintentionally. This alters flavor and increases acidity, Prompt processing preserves freshness and prevents defects. Cleanliness during processing is equally important. Equipment must be clean to avoid contamination. Even small residues can affect aroma and flavor. Attention to detail maintains consistency. Olive oil reflects the conditions under which the olives grew. Soil, climate, water availability, and tree health all influence the oil's character. Processing reveals these traits rather than masking them. Because olive oil is not refined, it carries a direct imprint of the tree and environment. Differences between harvests, locations, and varieties remain evident. This variability is accepted and valued. The transformation from fruit to oil represents a shift from solid to liquid without altering the essential nature of the olive. The oil is a concentrated expression of the fruit's chemistry. This concentration explains why olive oil carries strong flavor even in small amounts. Aromatic compounds and fats are preserved rather than diluted. The oil retains the olive's identity in a new form. Olive oil production also generates byproducts. Water and solids remain after extraction. Traditionally, these were returned to the land or used as fuel. Modern systems manage waste carefully to reduce environmental impact. The simplicity of olive oil production hides its precision. Each step must be controlled to preserve quality. Small deviations can produce noticeable differences in flavor and stability. From fruit to oil, the process respects the olive tree's slow work. Months of growth and resource accumulation are concentrated into a liquid that can be stored and shared long after harvest. Olive oil therefore represents time compressed. The tree invests seasons of growth. Humans extract that investment carefully, preserving what was built slowly. The act of pressing olives into oil connects modern practice to ancient methods. Although equipment has changed, the principles remain the same. Crush, mix, and separate without excess force. From fruit to oil, the olive's journey remains grounded in physical processes. Nothing is hidden or artificial. The oil is simply what the fruit contains, released and preserved. This transformation completes one of the olive tree's most valued contributions. The oil carries flavor, nutrition, and history in a stable form. The tree provides the raw material. Time and care shape the result. From fruit to oil, the process honors the olive tree's slow and deliberate nature. Olive oil's flavor and behavior come directly from its chemical composition. The most prominent component is fat, which makes up the majority of the oil. Unlike many other cooking oils, olive oil contains mostly monounsaturated fats. These fats are stable at room temperature and resist oxidation more effectively than polyunsaturated fats, contributing to both shelf life and cooking performance. Monounsaturated fats have a simple molecular structure that allows them to remain fluid while maintaining resistance to breakdown. This stability helps olive oil tolerate moderate heat without rapid degradation. It also explains why olive oil remains liquid at room temperature, but thickens slightly when cooled. Fat content also shapes how flavor is perceived. Fats carry aromatic compounds across the palate, allowing taste and smell to interact. As olive oil coats the mouth, volatile compounds are released gradually, creating layered flavor rather than a single sharp note. This slow release supports complexity and persistence. The flavor of olive oil varies widely depending on fruit ripeness. Olives harvested while still green produce oil with sharper, more intense flavors. These oils often taste grassy, peppery, or bitter. The bitterness comes from compounds preserved during early harvest, while pungency reflects the presence of specific aromatic molecules. Riper olives produce oils with milder, rounder flavors. As fruit matures, some bitter compounds decrease while oil content increases. This shifts flavor balance towards softness and richness rather than sharpness. Both styles reflect valid expressions of the fruit rather than quality differences. Bitterness and pungency are often misunderstood. In olive oil, these qualities indicate the presence of beneficial compounds rather than defects. Controlled bitterness provides structure and depth, preventing the oil from tasting flat. Pungency creates a warming sensation in the throat, reflecting the oil's chemical activity. Olive oil contains antioxidants that influence both flavor and stability. These compounds protect the oil from oxidation, slowing spoilage and preserving freshness. Antioxidants also contribute bitterness and complexity, linking taste directly to chemistry. The concentration of antioxidants depends on variety, growing conditions, and harvest timing. Olives grown under moderate stress often produce higher levels of these compounds. Stable but limited water availability can increase concentration, enhancing both flavor and shelf life. Processing plays a role in preserving chemistry. Lower temperatures during extraction protect delicate compounds from degradation. Excess heat can reduce antioxidant levels and flatten flavor. Careful temperature control allows the oil to retain its natural profile. Olive oil chemistry also includes minor compounds that influence aroma. These volatile molecules create scents associated with fresh grass, herbs, fruit, or spice. Although present in small quantities, they contribute significantly to sensory experience. Aroma compounds are sensitive to oxygen, light, and heat. Exposure during processing or storage can alter flavor. This sensitivity explains why proper handling and storage are essential to maintaining quality. The balance between fat, antioxidants, and aromatics defines an oil's character. Oils with high fat stability and preserved aromatics taste vibrant longer. Oils lacking these components degrade more quickly. Olive oil does not undergo refinement when produced properly. Mechanical extraction preserves natural chemistry rather than altering it. This directness means that flaws in fruit or processing are not hidden. The chemistry of olive oil also influences how it behaves in cooking. Stable fats resist breakdown, producing fewer harmful byproducts at moderate temperatures. This stability makes olive oil suitable for sautéing and roasting when used appropriately. Flavor changes during cooking reflect chemical reactions. Heat reduces some aromatic compounds while allowing others to emerge. Different olive varieties produce oils with distinct chemical profiles. Genetic differences influence fat composition, antioxidant levels, and aromatic compounds. These differences explain why oils from different regions taste unique. Climate and soil also shape chemistry. Sun exposure, temperature variation, and water availability influence compound formation. The oil carries a record of the environment in which the fruit grew. Storage conditions affect chemical stability after extraction. Light accelerates oxidation. Heat increases reaction rates. Oxygen exposure gradually degrades flavor. Proper storage preserves chemistry and extends usability. Fresh olive oil often tastes more vibrant because chemical compounds remain intact. Over time, even under ideal conditions, gradual oxidation softens flavor. This natural aging process reflects chemical change rather than spoilage. The chemistry of olive oil connects directly to health associations. Monounsaturated fats support lipid balance when consumed in place of less stable fats. Antioxidants contribute protective effects within the body. These benefits depend on preservation of chemical integrity. Flavor perception also interacts with human physiology. Bitter and pungent compounds stimulate sensory receptors, creating complexity. This interaction explains why olive oil can taste both sharp and smooth at the same time. Chemistry influences texture as well. Fat composition determines mouthfeel. Stable fats create a smooth, cohesive sensation rather than separation or greasiness. This texture supports culinary versatility. Olive oil's chemistry reflects the tree's slow growth. Compounds accumulate gradually within the fruit over months. This slow formation produces balance rather than extremes. Environmental stress influences chemical expression. Moderate stress often increases antioxidant concentration. Excess stress can damage fruit quality. Balance remains key. The relationship between flavor, fat, and chemistry explains why olive oil varies from year to year. Seasonal conditions alter compound formation. Each harvest reflects a unique combination of factors. The chemistry of olive oil does not aim for uniformity. Variation is expected and valued. Differences express origin rather than inconsistency. This chemical richness supports olive oil's cultural importance. Flavor, stability, and health associations combine to create lasting value. Olive oil remains a product shaped by biology rather than engineering. Its chemistry emerges from the fruit and environment rather than formulation. The tree provides raw compounds. Processing preserves them. Time reveals their interaction. Flavor, fat, and chemistry together define olive oil's identity. Each element supports the others. When balanced, the oil expresses depth and longevity. The chemistry of olive oil therefore completes another stage of the olive's transformation. From fruit to liquid, the tree's internal processes remain visible in taste and behavior. The olive tree's work continues in the oil it produces. Fat carries energy. Antioxidants preserve structure. Aromatics provide expression. Together, these elements make olive oil a concentrated reflection of the tree's long, patient life. Olive trees play a defining role in the landscapes where they grow. Across Mediterranean regions, olive groves shape hillsides, valleys, and coastal plains, becoming part of the terrain rather than standing apart from it. Their presence reflects adaptation to land that is often rocky, uneven, and exposed. Olive trees help prevent soil erosion, especially on sloped ground. Their root systems spread widely through shallow soil layers, binding earth that might otherwise wash away during winter rains. On hillsides, this stabilizing effect allows soil to remain in place despite gravity and runoff. The roots of olive trees also penetrate rocky terrain. Rather than requiring deep, fertile soil, olive trees anchor themselves among stones and fractured bedrock. This ability allows them to occupy land unsuitable for many other crops. Rocky ground that would limit root expansion in faster-growing plants becomes workable terrain for olives. Terraced landscapes developed alongside olive cultivation. Stone walls built into slopes create level planting surfaces and slow water movement. These terraces reduce erosion while capturing moisture during rain. Olive trees planted on terraces benefit from improved stability and drainage without requiring rich soil. Olive groves support diverse plant and animal life. Traditional groves often contain grasses, wildflowers, shrubs, insects, birds, and small mammals. This diversity creates layered ecosystems rather than monocultures. Olive trees coexist with other species, rather than excluding them. The open structure of olive trees allows sunlight to reach the ground beneath. This supports undergrowth that stabilizes soil and contributes organic matter. Fallen leaves, grasses, and plant debris gradually enrich the soil without intensive intervention. Olive trees tolerate poor soil conditions well. Fertility matters less than structure and drainage. Excess nutrients can encourage excessive leaf growth at the expense of fruit quality. Lean soils often produce more balanced growth and better olives. Drainage is critical in olive landscapes. Water must move away from roots rather than pooling around them. Hillsides and rocky soils naturally provide this drainage. In flat areas, careful land shaping is often required to prevent waterlogging. Too much water harms olive trees. Saturated soil restricts oxygen access to roots, increasing disease risk and weakening growth. Olive landscapes therefore prioritize water movement rather than retention. Moderate moisture combined with good drainage supports long-term health. Moderate environmental stress often improves olive quality. Trees growing in challenging conditions focus energy efficiently rather than producing excessive foliage. This restraint concentrates compounds in fruit and oil, shaping flavor and stability. Olive groves often coexist with wild species because olive trees do not require complete land clearing. Shrubs and native plants remain between trees, supporting biodiversity and reducing erosion. This mixed landscape contrasts with intensive agricultural systems that remove surrounding vegetation. The longevity of olive trees allows landscapes to remain stable over long periods. Groves planted centuries ago may still be productive today. Olive trees influence microclimates within landscapes. Their canopies provide light shade that moderates temperature and reduces wind at ground level. This protection benefits undergrowth and soil organisms. The spacing of olive trees reflects landscape adaptation. Trees are planted far enough apart to reduce competition for water while allowing air and light to move freely. This spacing supports both tree health and landscape stability. Olive landscapes are shaped by human care rather than machinery. Stone terraces, hand pruning, and selective planting reflect accumulated knowledge of terrain. These practices align with the olive tree's slow response and long life. The visual character of olive landscapes reflects endurance. Twisting trunks, silvery leaves, and irregular spacing create scenes that change slowly over time. Seasonal shifts appear subtle rather than dramatic. Olive trees contribute to long-term soil formation. Leaf litter and root turnover add organic material gradually. Over decades, soil structure improves even in marginal environments. Wildlife benefits from olive landscapes. Birds nest in branches. Insects inhabit bark and leaves. Small animals shelter among roots and stones. These interactions create functional ecosystems rather than isolated orchards. Traditional olive groves often persist because they remain economically viable without heavy inputs. Low water requirements and minimal fertilization allow continued use of land that might otherwise be abandoned. Olive landscapes connect agriculture with ecology. The tree's needs align with preservation rather than extraction. The presence of olive trees often determines how land is used. Settlements, paths, and terraces form around groves. The tree becomes a structural element in human geography. Over time, olive landscapes record environmental history. Changes in climate, land use, and management leave visible traces in tree form and spacing. Each grove reflects decades of interaction between tree and terrain. The resilience of olive landscapes comes from alignment. trees, soil, water, and human care operate together. When this alignment holds, groves endure. Olive landscapes are not accidental. They are the result of long observation and adaptation. Each placement reflects knowledge passed across generations. The olive tree's relationship with land mirrors its biology. Slow growth, tolerance of hardship, and long life shape how landscapes evolve around it. Olive trees anchor human activity without dominating it. They share space with wild systems while supporting agriculture. Olive trees in the landscape demonstrate how agriculture can work with land rather than against it. Stability emerges from cooperation rather than force. The landscape becomes part of the olive tree's life, just as the tree becomes part of the landscape's identity. Olive trees are closely adapted to the soils they inhabit, and their success depends more on structure and drainage than on fertility. Unlike crops that require rich, deep soil, olive trees tolerate poor, rocky ground remarkably well. What matters most is that water can move freely through the soil rather than collecting around the roots. Well-drained soil allows oxygen to reach the root system. Olive roots require air as much as moisture. When soil becomes compacted or waterlogged, oxygen is displaced and roots struggle to function. Prolonged saturation weakens root tissue and increases vulnerability to disease, even when water is abundant. Because olive trees evolved in dry, uneven landscapes, their roots are adapted to seek moisture efficiently without remaining submerged. Wide root systems spread through shallow soil layers, while deeper roots access stored moisture below the surface. This design supports survival during long dry periods while avoiding damage from excess water. Water availability influences olive growth directly. Consistent but limited watering supports steady development. Excess water encourages rapid leaf growth, which increases demand on the root system and reduces fruit quality. Too little water, however, forces the tree into survival mode, slowing fruit development and reducing yield. Moderate water stress often improves olive quality. When water is limited but not absent, olive trees focus energy on fruit rather than excessive vegetative growth. This restraint concentrates compounds within the olives, shaping flavor and oil chemistry later on. Controlled stress supports balance rather than damage. Soil composition also affects how water behaves. Sandy or rocky soils drain quickly, preventing prolonged saturation. Clay soils hold water longer and can become compacted, increasing risk if drainage is poor. In clay-heavy areas, careful site selection and land shaping are essential to protect olive roots. Soil depth matters less than soil stability. Olive trees do not require deep, uniform soil profiles. They tolerate shallow soils with underlying rock, anchoring themselves where fractures and crevices provide access to moisture. This allows olive trees to grow where other crops cannot establish reliable roots. Water stress interacts with temperature. During hot periods, water demand increases as evaporation accelerates. Olive trees manage this by reducing growth and limiting water loss, rather than increasing uptake aggressively. Leaves regulate transpiration, conserving internal moisture. When water becomes scarce, olive trees close stomata on their leaves to reduce evaporation. Photosynthesis continues at a reduced rate, allowing the tree to remain alive without exhausting reserves. This response protects internal systems during prolonged drought. Excess water creates different stress. Saturated soil interferes with nutrient uptake and root respiration. Leaves may appear healthy initially, but internal damage accumulates. Over time, growth slows, flowering declines, and disease risk increases. Stress also affects the tree's reproductive cycle. Water imbalance during flower formation or fruit development can reduce yield. Drought during flowering may limit fruit set. Excess water during fruit growth can dilute compounds and weaken fruit structure. Olive trees respond slowly to stress. Effects may not appear immediately, but can influence growth and production in subsequent seasons. A single year of severe stress can reduce flowering or yield several years later. This delayed response reflects the tree's long-term strategy rather than immediate failure. Soil management plays a key role in moderating stress. Maintaining ground cover between trees helps regulate soil temperature and moisture. Grasses and low vegetation reduce evaporation and prevent erosion without competing excessively for water. Organic matter improves soil structure over time. Fallen leaves and plant debris break down slowly, increasing soil porosity and supporting microbial life. Healthy soil organisms improve nutrient availability and root function. Over-fertilization can increase stress rather than reduce it. Excess nutrients promote rapid vegetative growth, increasing water demand and reducing resilience. Olive trees perform best when growth remains balanced rather than stimulated aggressively. Irrigation practices must align with olive biology. Frequent shallow watering encourages surface roots and reduces drought resilience. Deeper, less frequent watering supports strong root systems and long-term stability. Stress also influences disease susceptibility. Trees weakened by water imbalance are more vulnerable to fungal infections and insect damage. Maintaining proper drainage and moderate moisture supports the tree's natural resistance. Environmental stress interacts with pruning and canopy structure. Dense canopies increase water demand and trap humidity. Open structures reduce stress by improving airflow and light penetration. Soil, water, and structure must be managed together. Olive trees tolerate stress better than sudden abundance. Rapid changes in watering or soil conditions disrupt internal balance. Gradual adjustments allow the tree to adapt without shock. Seasonal rhythms guide stress response. Wet winters replenish soil moisture gradually. Dry summers slow growth and conserve resources. Olive trees evolved to rely on this predictable pattern rather than constant availability. Modern interventions that disrupt these rhythms often increase stress. Continuous irrigation during dry periods may prevent necessary rest, weakening long-term performance. Allowing moderate seasonal stress supports endurance. Soil erosion increases stress by exposing roots and reducing stability. Olive trees help prevent erosion through their root systems, but excessive disturbance undermines this protection. Maintaining ground cover preserves soil integrity. Stress is not inherently harmful to olive trees. It becomes damaging only when extremes persist or balance is lost. Moderate stress supports quality and longevity, while severe or prolonged stress compromises health. The tree's ability to regulate growth under stress allows it to survive conditions that would exhaust other species. This regulation supports long life and steady productivity. Soil and water conditions shape each stage of the olive tree's life. Roots establish stability, leaves manage loss, growth slows when needed, recovery follows when conditions improve. Stress therefore becomes part of the olive tree's rhythm rather than a threat. The tree responds, adjusts, and continues. Managing soil and water means respecting this rhythm. Interventions should support balance rather than override it. The relationship between soil, water, and stress defines where olive trees belong. They succeed where drainage is good, water is limited but reliable, and change occurs gradually. In these environments, olive trees continue their steady work. Stress is present but controlled. Soil, water, and stress remain in dialogue, shaping the olive tree's long, resilient life. Olive trees respond to water availability with a strategy shaped by survival rather than abundance. Their resilience depends on how water arrives, how long it remains available, and how gradually conditions change. Rather than thriving under constant moisture, olive trees perform best when water is limited but reliable, allowing internal systems to operate without excess strain. Consistent but restrained watering supports steady growth. When water is available in moderate amounts, olive trees maintain leaf function, support fruit development, and preserve internal balance. The tree grows within its capacity rather than exceeding it. Overwatering disrupts this balance. Excess moisture encourages vigorous leaf growth, increasing transpiration and water demand. Roots become accustomed to constant saturation, reducing their ability to function during dry periods. This dependency weakens resilience and increases vulnerability when water supply changes. Shallow, frequent watering creates surface-level root systems. Roots remain close to the soil surface, where moisture appears regularly. While this may support short-term growth, it reduces access to deeper water reserves and limits stability. During drought, surface roots dry quickly, leaving the tree under stress. Deeper, less frequent watering encourages roots to extend downward. Roots that reach lower soil layers access moisture stored beyond surface evaporation. This depth improves drought tolerance and allows the tree to remain functional during long dry periods. Over time, deep roots anchor resilience. Olive trees evolve to rely on seasonal water patterns. Winter rains replenish soil moisture gradually. Spring supports flowering and early fruit development. Summer dryness slows growth and conserves resources. This cycle allows the tree to rest without shutting down completely. When irrigation interrupts this pattern, the tree may lose its natural rhythm. Continuous watering during summer prevents necessary slowdown. Growth continues when it would normally pause, increasing demand on internal systems. Over time, this constant activity can weaken the tree rather than strengthen it. Resilience depends on the tree's ability to regulate itself. Olive trees close stomata to reduce water loss during dry conditions. Leaves remain intact, and photosynthesis continues at a reduced rate. This adjustment allows the tree to survive without exhausting reserves. Water stress also influences how the tree allocates energy. During dry periods, resources are directed toward maintaining vital tissues rather than producing new growth. This prioritization protects long-term survival and prepares the tree for recovery when moisture returns. Olive trees can endure extended drought without permanent damage when stress develops gradually. Sudden water loss, however, creates shock. Rapid shifts from wet to dry conditions strain internal systems and reduce the tree's ability to adjust. Gradual change supports adaptation. Resilience is also shaped by soil conditions. Well-drained soils allow roots to access oxygen even when moisture is present. Poor drainage suffocates roots, reducing their ability to absorb water effectively. In such conditions, even adequate watering fails to support health. Ground cover contributes to resilience by moderating soil temperature and reducing evaporation. Low vegetation shades soil surface, preserving moisture and preventing erosion. This support allows olive roots to operate more efficiently without competing excessively for water. Mulch and organic matter improve water retention while maintaining drainage. Over time, organic material increases soil porosity, allowing water to infiltrate without pooling. Resilience also involves recovery from damage. Olive trees can regenerate new shoots from old wood after pruning, drought, or fire. This regenerative ability allows the tree to restore structure gradually without requiring replacement. Recovery proceeds through steady regrowth rather than rapid repair. New shoots emerge slowly, filling gaps created by stress or intervention. This controlled regeneration preserves balance and prevents overextension. The tree replaces what was lost while maintaining overall stability. Water availability influences regeneration speed. Adequate moisture supports new growth, but excess water can encourage weak shoots that compromise structure. Balanced watering supports strong, gradual recovery. Olive trees respond poorly to abrupt changes in watering practices. Increasing water suddenly may trigger rapid leaf growth that the tree cannot sustain. Reducing water suddenly may cause stress before roots can adapt. Gradual adjustment allows internal systems to recalibrate. Resilience also depends on how water interacts with temperature. During heat, water loss accelerates. Olive trees limit damage by reducing growth and conserving moisture. Water availability supports this response but does not override it. In cooler periods, water demand decreases. Olive trees absorb moisture without stress, replenishing reserves. This seasonal adjustment reflects alignment between water availability and metabolic needs. Long-term care strengthens resilience by reinforcing these patterns. Trees managed with restraint develop deeper roots, balanced canopies, and efficient water use. These traits accumulate over years rather than appearing quickly. Short-term interventions often undermine resilience. Excess irrigation, heavy fertilization, or rapid growth stimulation may increase yield temporarily, but weaken the tree's ability to cope with stress later. Olive trees trade immediate output for endurance. Resilience also shapes fruit quality. Trees that experience moderate water stress often produce olives with higher concentrations of compounds. These compounds influence flavor and oil stability. Stress within limits enhances quality rather than reducing it. Watering practices therefore influence both survival and product. Managing water is not about eliminating stress, but about maintaining it within a tolerable range. Olive trees perform best when challenge and support remain balanced. Resilience is visible in the tree's form. Twisting trunks, irregular branches, and scarred wood reflect adaptation to past stress. These features do not indicate weakness. They record survival across changing conditions. Olive trees respond slowly to improvement. A tree weakened by years of poor watering does not recover in one season. Gradual restoration of balance allows internal systems to rebuild. Patience supports recovery. Resilience also depends on continuity. Trees managed consistently over time adapt to their environment. Sudden changes in practice disrupt this adaptation. Stability and care support stability and growth. Watering and resilience are inseparable. How water is delivered shapes root structure, canopy behavior, and stress response. Each decision influences future capacity rather than immediate appearance. Olive trees do not seek optimal conditions, they seek survivable ones. Their resilience comes from tolerance, adjustment, and conservation rather than from maximization. Managing water for olive trees means allowing them to respond naturally. Support is provided without excess. Stress is permitted without damage. Over decades, resilient trees remain productive through variability. They endure dry years, recover from damage, and continue growing within limits. Watering that supports resilience respects time. The tree responds slowly, but its response is lasting. Each season builds upon the last, shaping strength rather than speed. Resilience emerges from repeated alignment between water, soil, and growth. When these elements remain coordinated, olive trees continue their long work under changing conditions. The tree's ability to endure depends less on how much water it receives and more on how that water fits within its rhythm. Olive trees produce wood that reflects the same slow, deliberate growth seen in every other part of the tree. Olive wood is dense and tightly grained, formed over many years rather than through rapid expansion. This density gives the wood strength and durability, making it resistant to splitting and decay. The slow pace at which olive wood develops shapes both its physical properties and its response to use. The grain of olive wood is often irregular and richly patterned. Growth rings form gradually, creating swirls and variations rather than uniform lines. These patterns record changes in environment, water availability, and growth direction over time. Each section of wood reflects years of adjustment rather than a single season of expansion. Because olive wood grows slowly, it becomes hard and compact. This hardness makes it suitable for tools and objects that must withstand repeated use. Historically, olive wood was valued for its ability to endure wear without breaking down quickly. Handles, utensils, and small implements benefited from this resilience. Olive wood has been used for craft and art for centuries. Carvers valued its density and fine grain, which allowed detailed shaping and smooth finishes. The wood responds well to careful cutting, but resists sudden force. This behavior mirrors the tree's broader pattern of responding gradually rather than immediately. The use of olive wood required patience. Because the wood is hard, shaping it takes time and effort. Rapid cutting risks damage to tools and material alike. Skilled craftspeople learn to work slowly, allowing the grain to guide the process. Olive trees regenerate after damage in ways that support continued use of their wood. New shoots can emerge from old wood, even after heavy pruning or fire. This regenerative ability allows olive trees to recover structure without needing replacement. The tree rebuilds gradually, reinforcing existing systems. Regeneration does not happen quickly. New growth emerges slowly, strengthening over time. Shoots develop into branches only after years of steady growth. This slow response prevents imbalance and reduces the risk of weak or unstable structure. Olive trees are slow to respond to change in general. Alterations in environment, care, or structure do not produce immediate results. Whether conditions improve or worsen, the tree adjusts over seasons rather than days. This delayed response reflects internal systems designed for stability rather than speed. When olive trees experience stress, such as drought, pruning, or fire, recovery follows a measured pattern. Growth resumes cautiously. Energy is directed toward rebuilding essential tissues rather than producing excess growth. This restraint reduces the likelihood of failure during recovery. Fire illustrates this resilience clearly. Olive trees can survive fires that destroy above-ground growth, Living tissue beneath the bark often remains intact. After fire, new shoots may emerge from the trunk or base. Over time, these shoots form a renewed canopy, restoring the tree without erasing its history. This capacity to regenerate from old wood contributes to the olive tree's longevity. Damage does not necessarily end productivity. Instead, the tree incorporates scars and regrowth into its structure. Twisted trunks and hollow centers often reflect cycles of damage and recovery rather than decline. The slow response of olive trees means that mistakes persist. Severe pruning, improper cutting, or repeated stress can shape growth for decades. Recovery is possible, but it unfolds gradually. This reinforces the importance of restraint and long-term thinking. Wood density also influences how olive trees carry fruit. Strong branches support olives without bending excessively. Weight is distributed across sturdy limbs rather than thin, fast-growing shoots. This structure reduces breakage and supports consistent production. The relationship between wood and fruit reflects balance. Growth that is too rapid produces weaker wood that cannot support long-term productivity. Slow, dense wood provides stability for both canopy and crop. Olive trees respond to pruning by producing new shoots, but not in abundance. Growth is selective. Shoots emerge where structure allows, filling gaps without overwhelming the tree. This controlled response maintains balance. Craft traditions built around olive wood reflect respect for this slow growth. Wood was often harvested from pruned branches or fallen trees rather than cut from healthy trunks. This practice preserved living trees while making use of available material. The durability of olive wood also contributed to its symbolic value. Objects made from olive wood were associated with endurance and continuity. The material carried the tree's history into human use. Olive wood does not respond well to rapid drying or sudden changes in humidity. Like the living tree, the wood adjusts slowly. Sudden drying can cause cracking, while gradual seasoning preserves integrity. This behavior requires patience from those who work with it. The slow response of olive trees extends beyond wood into overall management. Trees do not show immediate improvement after care changes. Benefits appear gradually as internal systems adjust. This delayed feedback challenges short-term expectations. Because olive trees change slowly, they integrate care decisions over time. A single season rarely defines outcome. Instead, patterns emerge across years. This long view aligns with how the tree allocates resources and repairs itself. The connection between wood, craft, and slow response highlights the olive tree's approach to survival. Strength is built through accumulation rather than acceleration. Recovery follows measured steps rather than sudden bursts. Human use of olive wood reflects this same pattern. Craft respects material limits. Objects are shaped slowly and maintained carefully. Durability is valued over speed of production. The olive tree's slow response does not indicate weakness. It reflects a strategy that prioritizes endurance. The tree absorbs change, adjusts gradually, and continues functioning. Wood growth, regeneration, and response to stress all reflect this strategy. Olive trees survive because they do not react impulsively. They respond when conditions stabilize. The tree's structure records time visibly. Each curve, hollow, and branch reflects adaptation. These features tell a story of resilience shaped by patience. Olive trees continue growing within limits defined by their biology. Wood strengthens slowly. Response unfolds over years. Craft and care align with this pace. This slow response supports stability across centuries. The olive tree remains productive, adaptable, and present despite changing conditions. Wood, craft, and slow response form a connected system. Dense wood supports structure. Regeneration preserves form. Gradual adjustment protects longevity. Together, these traits explain how olive trees endure. They build strength slowly, respond carefully, and remain resilient through time. Olive trees hold strong cultural and symbolic meaning that developed alongside their long history of cultivation. This meaning did not arise from appearance alone, but from how olive trees behave over time. Their slow growth, long life, and steady productivity shaped how people understood endurance, continuity, and restraint. Olive trees are often associated with peace because they persist without aggression. They do not spread rapidly or overwhelm surrounding plants. Instead, they remain rooted, growing gradually within their environment. This quiet persistence made olive trees symbols of stability in regions shaped by conflict, migration, and changing borders. The olive branch became a symbol of reconciliation long before it was adopted into formal traditions. After periods of conflict, olive groves often remained standing, even when other structures were destroyed. Trees that continued producing fruit after hardship represented the possibility of renewal without erasing the past. This symbolism emerged from direct observation. Olive trees survive drought, fire, and neglect better than many crops. They recover slowly but reliably. People learned that damage did not always mean loss. New growth could emerge from old wood. Production could return after difficult years. These traits shaped how olive trees were understood beyond agriculture. Ancient civilizations valued olives as both food and fuel. Olive oil was essential for cooking, lighting, and personal care. Lamps fueled by olive oil extended activity into evening hours, shaping daily rhythms. This practical importance strengthened symbolic value. Olive trees supported life in visible, repeatable ways. Olive oil also played a role in medicine and ritual. Its use in healing practices reflected belief in its sustaining qualities. Oil was applied to skin, wounds, and hair, reinforcing its association with preservation and care. These uses tied the olive tree to physical well-being as well as sustenance. The centrality of olive oil in daily life reinforced respect for the tree itself. Because oil production required years of growth and careful processing, olive trees were not treated as disposable resources. They were maintained across generations, shaping family identity and land inheritance. Olive trees became markers of continuity in a changing world. Groves planted by one generation often remained productive for descendants centuries later. This long-term presence allowed olive trees to connect past and present without interruption. Symbolism also developed through restraint. Olive trees do not produce immediate rewards. Years pass before meaningful harvests occur. This delay reinforced associations with patience and foresight. Those who planted olive trees often did so, knowing they might never see full production themselves. This long horizon shaped cultural values around planning and stewardship. Olive cultivation encouraged thinking beyond immediate need. Care given today influenced outcomes far into the future. Olive branches symbolized peace because they reflected this forward-looking restraint. Offering an olive branch implied commitment to stability rather than dominance. The symbol represented continuity rather than conquest. The endurance of olive trees through hardship reinforced these meanings. Trees damaged by war or fire often regenerated. Their continued presence served as reminders that recovery was possible without erasing history. Olive trees were also central to early trade networks. Oil and preserved olives moved across regions, connecting communities. Trade expanded cultural influence while reinforcing shared reliance on the same tree. This shared dependence strengthened symbolic meaning across borders. The spread of olive cultivation shaped settlement patterns. Communities formed around groves that provided reliable resources. Olive trees became anchors within landscapes, influencing where people lived and how land was organized. Because olive trees required minimal water and tolerated poor soil, they supported habitation in marginal environments. Their presence made certain regions viable for long-term settlement. This role linked olive trees to survival and adaptation. Cultural meaning was reinforced through repetition. Each harvest season renewed the connection between people and trees. Rituals, labor, and shared work embedded olives into collective memory. Olive trees were often protected by custom or law. Damaging a productive olive tree carried social consequences. This protection reflected recognition of the tree's long-term value and irreplaceability. Symbolism extended into art and language. Olive branches appeared in carvings, coins, and stories. These representations drew from everyday experience rather than abstract ideals. The tree's physical traits informed its meaning. The olive tree's twisted trunk and persistent foliage reinforced associations with endurance. Visible age and survival marked time in ways few other plants could. The tree became a living record rather than a fleeting presence. Cultural symbolism did not separate the olive tree from its agricultural role. Meaning emerged because the tree worked reliably over long periods. Symbol and function remained aligned. Olive trees were not romanticized as delicate or fragile. Their symbolism rested on resilience rather than beauty. They endured heat, drought, and neglect. This durability made their survival meaningful rather than ornamental. The association with peace also reflected restraint. Olive trees do not dominate ecosystems. They coexist with other plants and animals. The olive branch symbol gained strength because it reflected lived experience. Peace, like olive cultivation, required patience and long-term commitment. Both depended on sustained care rather than force. Olive trees also became symbols of endurance within families. Groves were passed down, maintained through generations. The tree's long life mirrored family continuity. This generational connection reinforced responsibility. Decisions made by one generation affected many others. Olive trees made the consequences of care or neglect visible across time. Cultural meaning also developed through loss. When olive trees were destroyed, recovery took decades. This vulnerability deepened appreciation for preservation. People learned that some losses could not be quickly repaired. Olive trees thus became symbols of what deserved protection. Their slow response to damage made them reminders of irreversible change. The olive tree's cultural role remains active rather than historical. Modern societies continue using olive branches and oil as symbols of peace, continuity, and endurance. These meanings persist because the tree still behaves the same way. The symbolism has not drifted from reality. Olive trees continue growing slowly, producing fruit steadily, and recovering gradually from stress. Their behavior remains consistent with the meanings attached to them. Culture and symbolism around olive trees reflect long observation rather than invention. The tree taught people how to think about time, restraint, and recovery through its presence. Olive trees did not become symbols through myth alone. They became symbols because they endured. Their value lies in what they demonstrate repeatedly. Care accumulates. Patience matters. Recovery is possible when growth is allowed to proceed within limits. Culture captured these lessons and passed them forward. The olive tree became a reference point for continuity in a world of change. Symbolism surrounding olive trees remains grounded in physical reality. The tree continues doing what it has always done. Culture responds by remembering. Olive trees played a central role in early trade because they produced goods that could be stored, transported, and exchanged over long distances. Olives themselves could be cured and preserved, while olive oil could be kept in sealed containers for extended periods without spoiling. This durability made olives and oil reliable commodities in regions where fresh food was seasonal and unpredictable. Early trade networks developed around these qualities. Olive oil moved along coastal routes and inland paths, connecting settlements across the Mediterranean. Because oil was lightweight, relative to its value, and resistant to spoilage, it traveled more easily than many other agricultural products. These practical advantages shaped how trade expanded and where routes formed. The movement of olive oil influenced settlement patterns. Communities often formed near groves to secure access to production. Towns developed around pressing sites, storage facilities, and ports. Olive trees anchored economic activity to specific landscapes, encouraging long-term habitation rather than temporary use. Trade encouraged specialization. Some regions focused on growing olives, while others refined oil, produced storage vessels, or managed transport. This division of labor strengthened regional identities and linked distant communities through shared dependence on olive products. Olive oil became a standard unit of value in many areas. Its consistent quality and usefulness allowed it to function as a medium of exchange alongside other goods. This role reinforced the tree's economic importance and integrated it into everyday transactions. Settlement stability followed olive cultivation. Because trees required years to mature, growers committed to land long-term. This discouraged frequent relocation and promoted investment in infrastructure such as terraces, roads, and storage buildings. Olive trees encouraged permanence. The long lifespan of olive trees also shaped land ownership. Groves passed between generations, becoming family assets rather than short-term investments. Trade routes adapted to olive production cycles. Harvest seasons influenced transport timing. Storage allowed flexibility, but pressing and distribution followed predictable rhythms. Markets aligned with these cycles, integrating agriculture into broader economic systems. Ports became focal points for olive trade. Coastal settlements with access to shipping routes gained importance as distribution hubs. Inland groves relied on these ports to reach wider markets. This relationship connected rural landscapes with urban centers. Olive oil's versatility increased demand. It was used for food, lighting, medicine, and ritual. These diverse applications ensured steady trade, even when one use declined. Demand remained consistent across social classes, supporting widespread distribution. The need to transport oil safely influenced container design. Clay amphorae and later vessels were shaped to protect contents during travel. Standardized container sizes supported trade efficiency and taxation. Trade also spread olive cultivation beyond its original regions. As demand grew, olive trees were planted in new areas with suitable climates. Settlers carried cuttings and knowledge along trade routes, extending cultivation gradually rather than rapidly. Settlement expansion followed ecological limits. Olive trees thrived only where climate and soil allowed. Trade did not override these constraints. Instead, it concentrated activity in regions aligned with the tree's requirements. Trade networks reinforced cultural exchange. Along with oil and olives, ideas, techniques, and traditions moved between regions. Pressing methods, curing practices, and grove management evolved through shared experience. The economic importance of olives influenced political structures. Control of productive groves and trade routes became sources of power. Protection of olive trees was often enforced by law, reflecting recognition of their long-term value. Conflict disrupted trade, but rarely erased olive cultivation entirely. Trees often survived upheaval, allowing production to resume when stability returned. This resilience supported economic recovery after disruption. Settlement patterns shaped by olive trade persisted for centuries. Roads, ports, and towns developed in relation to groves remained active long after their founding. Olive trees outlasted many of the systems built around them. The slow pace of olive cultivation influenced trade expectations. Returns accumulated gradually. Wealth derived from olives reflected sustained production rather than rapid exploitation. This tempered speculative expansion. Smallholder production remained common even as trade expanded. Olive groves could be managed by families rather than large estates. This distributed production reduced risk and supported community-based economies. Trade connected small producers to distant markets. Olive oil pressed in rural groves reached cities and foreign ports. This connection tied local labor to global demand without requiring industrial scale. Settlement around olive groves also shaped land use patterns. Terraces, paths, and irrigation systems followed tree placement. The landscape adapted to the tree rather than the tree adapting to the landscape. Trade in olive products encouraged preservation of groves. Destroying trees undermined long-term economic value. This encouraged protection rather than replacement, reinforcing continuity. Over time, olive trade became embedded in regional identity. Certain areas became known for their oil, shaping reputation and demand. Geographic association added value beyond volume. Settlement stability allowed knowledge accumulation. Techniques improved slowly as experience compounded. Trade rewarded consistency rather than novelty, reinforcing careful management. The relationship between trade and settlement reflected balance. Olive trees provided reliable output without encouraging overexpansion. Trade scaled within limits set by biology and climate. Settlement patterns anchored by olives proved resilient. Communities rebuilt around existing groves after disruption. The tree provided continuity even when institutions changed. Trade also reinforced social bonds. Harvesting, pressing, and transport required cooperation. Shared labor supported collective stability. The olive tree's influence on trade and settlement arose from its slow, dependable nature. Its products could be stored and exchanged. Its cultivation required commitment. Trade followed the tree rather than forcing it. Settlements formed where olives could grow. Roots developed to move what the tree produced. Trade and settlement patterns built around olives reflect long-term thinking. They prioritize sustainability over rapid extraction. The olive tree's role in trade connected distant places while anchoring people locally. This dual effect shaped enduring landscapes. Settlement around olive groves created continuity. Trade extended that continuity outward. Together, trade and settlement reveal how olive trees shaped human movement and permanence. The tree did not follow trade, trade followed the tree. Olive trees change slowly, and their form reflects the passage of time more visibly than many other cultivated plants. As years accumulate, trunks thicken, twist, and often become hollow at the center. These changes are not signs of decline. They are the result of long-term adaptation to environment, stress, and repeated cycles of growth and recovery. Olive trees age gradually and visibly. Unlike trees that grow quickly and then weaken, olive trees build structure over decades. Growth rings form slowly, reinforcing wood rather than stretching it thin. This gradual strengthening allows the tree to carry its own weight, even as form becomes irregular. With time, many olive trunks develop hollows. Internal wood may decay, while living tissue remains active around the outer layers. Water and nutrients continue moving through these living channels, allowing the tree to function even when the interior no longer supports transport. This adaptation allows olive trees to survive damage that would kill other species. The twisting shapes of olive trunks emerge from repeated response to stress. Wind, uneven light, pruning, drought, and regeneration all influence growth direction. Rather than growing straight and uniform, the tree adjusts incrementally. Each bend reflects a past condition rather than a design flaw. Scars on olive trees record environmental history. Fire damage, pruning cuts, frost injury, and broken branches leave marks that remain visible for decades. New growth often emerges around these scars, integrating damage into the tree's structure rather than replacing it entirely. Old olive trees frequently develop unique forms. Branches may extend asymmetrically. Trunks may split and rejoin. These forms reflect adaptation rather than randomness. The tree grows where conditions allow and reinforces what remains functional. Adaptation in olive trees is cumulative. Each response builds upon previous structure. The tree does not reset after stress. Instead, it incorporates experience into its form. This process produces individuality among trees even within the same grove. Environmental stress shapes adaptation. Drought limits growth rate. Wind influences branch orientation. Heat affects leaf density. The tree adjusts to these factors gradually, maintaining function rather than optimizing appearance. Olive trees tolerate repeated stress because they regulate growth conservatively. When conditions worsen, growth slows. When conditions improve, growth resumes cautiously. This moderation prevents exhaustion and allows recovery over long periods. Adaptation also occurs below ground. Root systems expand into available spaces, following moisture and stability rather than symmetry. Roots adjust depth and spread based on soil structure and water availability. This flexibility supports long-term anchoring. The visible aging of olive trees reflects stability rather than fragility. A tree that has survived centuries has adapted repeatedly. Its form carries evidence of those adaptations. Twisting trunks and hollow centers indicate resilience rather than weakness. Time influences productivity as well. Older olive trees may produce fewer olives by number, but fruit quality often remains high. Oil concentration and flavor complexity can increase as trees age. This reflects stable internal chemistry rather than declining function. Adaptation also affects canopy shape. Older trees often carry open crowns with irregular spacing. This structure improves airflow and light penetration without deliberate design. The tree adjusts canopy form naturally in response to internal and external pressures. Olive trees adapt to pruning over time. Rather than responding with rapid regrowth, they produce new shoots selectively. This slow response preserves balance and prevents excessive strain. Over years, pruning shapes form without forcing change. Fire adaptation illustrates resilience clearly. Olive trees can regenerate from old wood after fire removes above-ground growth. New shoots emerge from the base or trunk, rebuilding structure gradually. This ability allows survival in fire-prone landscapes. Adaptation does not erase history. Regenerated growth grows around existing structure. Old scars remain visible. The tree integrates new and old rather than replacing itself entirely. Time also influences how olive trees respond to human care. Improvements in soil, water management, or pruning do not produce immediate results. Benefits appear over seasons as the tree adjusts internally. This delayed response reinforces long-term planning. Adaptation extends to seasonal rhythms. Olive trees synchronize growth, flowering, and fruiting with predictable patterns. When climate shifts gradually, the tree adjusts timing slowly. Rapid or erratic change creates stress because adaptation cannot keep pace. The form of olive trees reflects this measured adjustment. Branch angles, leaf density, and growth direction all change incrementally. The tree responds where pressure exists, reinforcing successful structures. Olive trees do not aim for efficiency in the short term. Their adaptation prioritizes survival across uncertain conditions. Growth decisions reflect conservation rather than optimization. Adaptation also influences how olive trees interact with their environment. Open structure allows coexistence with other plants and animals. The tree does not dominate space aggressively. Instead, it occupies a stable position within the ecosystem. Time allows olive trees to adjust to human landscapes. Terracing, pruning, and cultivation shape growth slowly. The tree incorporates these influences without losing identity. Each olive tree becomes a record of interaction between biology and environment. Form reflects climate, care, and disturbance accumulated over decades or centuries. This visible history creates connection between people and trees. Old olive trees are recognized as living witnesses to past conditions. Their form carries meaning because it reflects endurance rather than perfection. Adaptation also explains why olive trees resist replacement. A mature tree embodies decades of adjustment. Removing it discards accumulated resilience. New trees require years to develop comparable stability. Olive trees are among the longest-lived cultivated plants, and their longevity is the result of steady processes rather than exceptional moments. From the beginning, the tree grows in a way that favors continuity over speed. Roots spread gradually, wood thickens slowly, and leaves remain in place year after year. These traits allow the tree to remain functional across long spans of time without requiring replacement. Longevity in olive trees does not mean uninterrupted growth. Periods of stress, damage, and recovery are woven into the tree's life. Drought slows development. Fire or pruning removes structure. Cold interrupts activity. The tree responds by conserving energy and rebuilding only what is necessary. Over time, these responses accumulate into a form that reflects survival rather than uniformity. Continuity depends on the tree's ability to persist without exhausting itself. Olive trees regulate production carefully. Flowering is abundant, but fruit set is limited. Heavy harvests are followed by lighter years. The tree does not aim for constant output, it aims for endurance. The physical structure of old olive trees illustrates this balance. Trunks may twist, split, or hollow, yet living tissue continues transporting water and nutrients along the outer layers. Branches adapt to shifting weight and light. Leaves remain functional despite changes in form. The tree continues operating even as structure evolves. Olive trees connect people to long-term thinking. Planting an olive tree is an investment measured in decades rather than seasons. Care given early influences outcomes far into the future. This long horizon shaped agricultural traditions built around patience, maintenance, and restraint. Continuity is also expressed through landscape. Olive groves persist where other forms of agriculture cycle rapidly. Terraces, paths, and tree spacing remain stable across centuries. The tree's needs align with preservation rather than constant renewal. Land adapts around the tree rather than being reshaped repeatedly. The olive tree's resilience supports this stability. When damage occurs, recovery proceeds slowly but reliably. New shoots emerge from old wood. Growth resumes when conditions allow. The tree does not replace itself quickly, but it does not surrender function easily. Longevity is reinforced by moderation. Olive trees tolerate stress, but not extremes. They thrive where water is limited but dependable, where sun is abundant but winters are mild. These narrow requirements restrict expansion, but support long life within suitable environments. Continuity also depends on consistent care. Olive trees respond poorly to sudden change, but adapt well to steady management. Pruning, watering, and harvesting shape growth over years rather than weeks. Results appear gradually, reinforcing long-term responsibility. The tree's slow response protects it from rapid depletion. Growth slows when resources are scarce. Production adjusts to conditions rather than forcing output. This restraint allows internal systems to remain aligned over time. Olive trees embody persistence through adaptation. They do not resist change aggressively. They incorporate it. Damage becomes structure. Stress influences form. Recovery integrates into existing systems. The continuity of olive cultivation reflects this biological strategy. Families tended the same groves across generations because trees remained productive when cared for steadily. Knowledge accumulated slowly, shaped by observation rather than instruction. Practices endured because they aligned with how the tree behaves. The olive tree's longevity also influences how its products are valued. Olives and oil carry the imprint of years of growth and care. Quality reflects accumulated balance rather than immediate intervention. This connection reinforces respect for time in both cultivation and use. Continuity does not imply stagnation. Olive trees continue adjusting subtly as conditions change. Roots expand into new spaces. Canopies shift with light. Production adapts to climate patterns. The tree remains active without pursuing rapid transformation. The final stage of the olive tree's cycle unfolds quietly. Fruit matures gradually. Oils accumulate slowly. Harvest interrupts a process that would otherwise continue without urgency. After harvest, the tree returns to maintenance, preparing for the next season. This cycle repeats across years without spectacle. Each season builds upon the last. Continuity emerges from repetition rather than climax. The tree's life advances through accumulation rather than milestones. Longevity allows olive trees to absorb variability. Dry years, heavy harvests, or periods of neglect do not necessarily end productivity. The tree adjusts, recovers, and continues. This resilience supports presence across long spans of human history. Olive trees connect modern life to ancient agriculture through function rather than symbolism alone. The same biological processes operate today as they did thousands of years ago. Roots draw water, leaves manage light, fruit develops slowly, oil is pressed carefully. Continuity persists because behavior remains unchanged. The olive tree's long life depends on alignment between environment, biology, and care. When these remain coordinated, the tree endures. When disrupted, recovery is possible, but slow. This pace reinforces respect for balance. Continuity also shapes expectation. Olive trees do not promise immediate return. They offer stability over time. This promise has guided how people relate to them across cultures and eras. As the olive tree ages, its form records adaptation. Each curve and hollow reflects adjustment rather than decline. The tree remains present because it changed gradually rather than resisting change outright. Longevity in olive trees is therefore not passive. It is active persistence shaped by restraint, regulation, and recovery. The tree survives by limiting excess and responding carefully to conditions. The olive tree's continuity does not depend on perfection. It depends on survival through variability. This survival reflects the success of its slow, deliberate strategy. As one season ends, the tree does not conclude. It remains in place, maintaining structure and function, ready to continue when conditions allow. Continuity unfolds without emphasis. Thank you for listening to the Sleepy Mind channel. I hope you have enjoyed spending time learning about the olive tree.